Okay, today we're going to be going over EE471 for the midterm review. And so we're going to start with compensators and what they are. And so compensator, basically we have an input here, R of S, and then it's going to go through to our summing block. And so we're used to seeing that. And it's going to have a compensator here known as GC of S. And so that's your compensator. So basically what that's doing is it's going to help to adjust your system so it's stable. And then it goes through a process which is known as G of S, and then it goes to the output, which is Y of S. And so there's a feedback path here, and we no longer feedback, we have H of S, and then this goes back to our input stage. And so that's basically the main role of the compensator. What we're going to be working with is right here, this block, known as the compensator block. And that's to compensate for like deficiency and performance. And so it's going to alter the shape of the root locus, what we're going to notice here, because we want to pull the root locus over to the left-hand plane to keep it more stable. And so our compensator is written in the following format. GC of S is equal to, and then it's going to be K times S plus Z over S plus P. That's the usual format of a compensator, because it has a zero and a pole we're going to introduce. This is known as a first order compensator because there's one order in the denominator. And so what you'll notice is for zero order, so I'm just going to go over zero order compensator, that would just be GC of S is equal to some constant K. A first order means that you have one pole. And so GC of S is going to equal K times S plus Z over S plus B. You just need one pole. And then a second order compensator, basically that just means you have two poles. And so what we'll see here is you can have an S plus Z1, S plus Z2, and then an S plus P1, S plus P2. And so just you have two poles here. That's the main difference instead of one. So that's why it's known as second order. Okay, so what we see here is there's two types of compensators. There's lead and there's lag. And so that's what we're going to be able to tell. So the first one that we usually focus on is phase lead. And so in lead, I always think positivity. You're leading ahead of everyone else. You're positive. So P comes before Z, which comes before zero. And so that means that the pole comes first, positivity, leading ahead of everyone else if you're positive. And so you're going to have your pole and then your zero. So notice that the zero is closer to the J omega axis here. And since it's closer to the J omega axis, it's going to be dominant. And so this zero is dominating. So the zero dominates since it's closer. And so it's going to pull the root locus to the left-hand plane. So that makes it stable. So we usually use phase lead because it pulls it over a left-hand plane, makes it stable. It's used for the transient response. And when we talk about transient response, that's like rise time, settling time. It makes the system faster. Whereas phase lag here, what we're going to have is if you're lagging behind people, I think you're failing. So the zero, you get a zero on your exam. Zero comes first, then the pole, then your zero. So what we're going to see here is your zero comes first, then your pole. So this is going to be the pole dominates. And if your pole dominates, it's going to push the root locus into the right-hand plane. So it pushes root locus into right-hand plane. And so this is going to be only used for steady state performance. So that means like steady state air. So decreasing the amount of air you have in your output. And so that's pretty much what we want to try and get. And so what we're going to notice here is we're going to try and make our system so that we make it stable. And so the phase lead design, basically what we're going to do here is there's a little bit of a process when you do phase lead. So for phase lead design, what we need to do, because this is dealing just with root locus right now, is remember, for your phase lead, your GC of S is equal to K S plus Z over S plus B. We normally just deal with first order compensators. And so remember, phase lead, the pole comes first. And so we're going to find the root locus for the uncompensated system. And you usually do that for all types. Even when you're doing design of Bode plots, you find first the uncompensated system, the root locus for the uncompensated system. And we often refer to that as L1 of S is equal to G of S times H of S. So the uncompensated system, the open loop gain, if you don't have a compensator because you haven't added the compensator yet, it's just G of S times H of S. So that's our L1 of S, the uncompensated system. You first find the root locus. And then after that, you're going to determine the desired closed loop. And these are going to be your dominant poles. These are going to have the most amount of effect on your system. So the dominant poles, so your closed loop poles, locations. And so when I talk about these, when you determine, this is going to refer to S1 and S1 conjugate that give the desired transient response. Okay. Now that we talked about that, basically we want to satisfy all the conditions that the problem's telling us. So like the rise time, the settling time, this is what you do. You determine where your dominant pole should be on that root locus to satisfy your requirements. And then third, you need to calculate the angle. So S1, your dominant pole, is on the root locus. So what we're going to see here is your overall angle of LS1. So basically your entire open loop gain would be GC of S, G of S, and H of S, right? And so what we're going to see here specifically is this is going to be the angle of the compensator and the angle of the uncompensated system, right? Because this is the uncompensated system, this is the angle of the compensator. So that's your total open loop gain. And so in order for it to be on the root locus, basically what you have to remember is when you go back to that characteristic equation where you have 1 plus k L of S is equal to 0, if you move that over, so you get the -1 on here. Remember, -1, if you take the angle of this, it's basically just going to say your angle of L of S is going to equal, and then here it would be 2r plus 1 times pi. And so that's what we have here because that's how we represent it. It's pi, and just keep repeating pi and you're going to get. And because if R0, you're at pi. So pi is -1 on the unit circle. And so what we're going to have here is on the right-hand side, it's going to be 2r plus 1 pi. Okay, so that's just from our characteristic equation, how this one was set equal to pi, and just the 2r plus 1 repeating around. So if you basically have r equal to 0, you'll be at pi. If you have r equal to -1, you have negative pi, same angle. So now what we have to do is we have to determine the angle of our compensator, which if you just move L1 of S1 over to the right-hand side, you're going to have 2r plus 1 times pi minus angle of L1 S1, okay? So that's pretty much the angle required. And so then you have to find, so here I like to say, what you do here, I diverge a little from what he says, is you're going to choose Z under S1. And so you know what I mean there, and then calculate P. And calculate P, and we're going to know basically what we're going to do here is remember your compensator, the angle of your compensator is going to equal, and then it's going to be the angle of your zero. So S1 plus Z, and then minus the angle of your pole, S1 plus P. That is the angle of your compensator. And so that's what we're going to see here specifically is when you find out what GC of S1 is equal to, if you need to now solve for your pole because you chose your zero, that was your 1 degree of freedom. If you solve for your angle of S1 plus P, it's going to equal here. Then if you move this over left-hand side, it'd be angle of S1 plus Z minus angle of GC of S1. And so GC of S1 is calculated from up here. So you plug in the number here, and then you just, the angle of your zero, if you choose the zero to be right under S1, because you chose it right under, it's going to be an angle of 90 degrees. And then minus your angle of GC of S1 is going to equal your angle of S1 plus P. So if you choose Z right under, it'd be a nice angle of 90. So we'll see that. And then your fifth step here is going to be choose K, because now you choose the amount of gain you're going to have within that compensator, such that, and then what we're going to have specifically is your, if you take the magnitude. So here, if we took the magnitude of this, what we would have seen is, remember, our angle of L of S is equal to the compensator times the uncompensated system. So finding the magnitude of all those parts individually. So for the compensator, it's going to be the magnitude of the numerator over the magnitude of the denominator. So that's why we have this part here. And then we're going to have times the magnitude of the uncompensated system and set that all equal to 1. And so that literally just comes from our equation over here. If you look at specifically how this is designed here, the characteristic equation, if we're just looking at the magnitude part, it's going to be, I just wrote the K outside of the L of S, but if you include the K within the open loop system, it's just telling you that the magnitude of L of S is equal to the magnitude of -1, which is just 1. And then remember, your L of S is going to be the magnitude of your GC of S, and then times the magnitude of the uncompensated system, and then equal to 1. And so that's how this equation, if your GC of S is your K, and then the S1 plus C over S1 plus B, and then times the magnitude of your uncompensated system. Okay, so now that we get that, we're going to solve an example in order to try and understand this. So we have all these rules, so let's look at how we're going to apply them. So for this example, it says for the system, so we're going to have the following. R of S, our input signal, it's going to go through a summing block here. Then we're going to have our compensator, GC of S. And within this compensator here, what's going to occur is we're going to have a 1 over S squared as our actual system here. And then we're going to have it go to the output signal, G or C of S. And then this is going to feed back all the way. So what it says is, it says the design requirements that we need to meet are the following. We're going to have the settling time less than or equal to 4 seconds. And we're going to have the percentage overshoot is less than or equal to 35%. So what we need to do is remember, our settling time is equal to 4 over zeta omega n. So that must be less than or equal to 4. And so we know if you just multiply zeta omega n, it would be greater than or equal to 4 over 4, 1. And so multiply both sides by a negative number, a -1, that flips the sign. And so we have negative zeta omega n less than or equal to -1. And then our percentage overshoot less than 35%. What we're going to see specifically from here is if our percentage overshoot, this would be zeta is going to have to be greater than or equal to. And then if we look at our table for the values of zeta, let me pull that up. Our zeta, if we want to achieve, it has to be greater than or equal to 0.3. Yeah, so that's what we have. So just if you look at that table for your zeta values, and so that's what we know. And then remember, your zeta is equal to your cosine of theta. So if you solve for theta, that's equal to cosine inverse of zeta. Okay, so right here, your theta has to be less than or equal to cosine inverse of 0.3. And if you do this on your calculator, cosine inverse of 0.3, doing that in degree zone, I get your theta needs to be less than or equal to 72.5 degrees. Okay, so those are just the requirements we have to meet. So if we plot this real quick, remember your negative zeta omega n here is on, so that's -1. So let's just say that's right about here. So it has to be less than, so it's going to be everything over to the left-hand side, and your angle is less than or equal to 72.5. So here. And this is your angle. Okay, so in order to meet both those design requirements, you have to be to the left of -1 and you have to be under 72.5. So that region where both conditions are met are the following. So that's what we're going to see. So remember step number one is we're going to find the root locus of the uncompensated system. When we're designing phase lead. So here's where L1 of S, that's what we need to plot. So our uncompensated system without the GC of S for the open loop gain is just our L1 of S is literally equal to, what we're going to see here, it's just 1 over S squared, correct? There's no other feedback term, and we don't include the compensator in this open loop gain. And so we need to find the root locus of this. So let's go to MATLAB. And when we go to MATLAB, so we're going to say that S is a transfer function of S. And then we're going to say that our L1, which is our uncompensated system, is equal to 1 divided by S squared. Oops, 1 divided by S squared. And then we need to plot the root locus of this. So I'm going to say our locus of R1. But what I'm actually going to do here is I need to open up Control System Designer, which will plot the root locus and the step response. And so I'm going to call it Control System Designer of this here. And so it's running for me. So we need to enter in our design requirements, which we remember our design requirements was our settling time less than 4 and our percentage overshoot grade less than 35%. And so here, while it's pulling up, it should pop up with Control System Designer soon. If not, I'll just call it again. Give it about 30 seconds real quick. There we go. Okay, so we don't need the Bodhi plot. We're just looking at root locus right now. So I'm going to close the Bodhi editor. And then we have to enter in our design requirements here. So for our root locus, we right click and hit design requirements new. And so for a design requirements, settling time is going to be less than 4 seconds. Then we need to enter in a new design requirement where we're going to put the percentage overshoot less than or equal to 35%. Okay. And then here for my step response, we have to make sure those design requirements are met as well. So I'm going to right click my step response. Let me put these side by side. And so let me put this over here. And so for my step response here, I'm going to want to add a design requirement. So let me look into it real quick. Oh, I don't want to click a point. Let me delete that. Delete that. So we need to satisfy our design. So let me just zoom in real quick on this part. Okay, so I need to add a point here. So I'm going to hit design requirements. I just zoomed in so it wouldn't touch a point there. And so because our settling time has to be less than 4 seconds, you have to make the rise time less than the settling time or you'll get an error. So I'm going to make it less than 4 seconds and my percentage overshoot less than 35%. Okay. So that was entered here. And so now in my step response graph, let me zoom out again, back to the original. Okay. So basically, I need to zoom back to what I originally had here. So I satisfy both. So basically, once you, I don't know exactly when the home screen's not on here, but what we have to do is we have to determine our polls so that we satisfy both of these. So if we're to satisfy both the step and specifically our root locus plot, what we're going to notice here is that white area is the region in which you can operate in. So basically here, what we're going to tell is that we need to have our graphs so that we can satisfy both conditions. And so what we're going to see basically in the root locus plot here is we have to pick to the left of -4, it looks like. And then we have to have our graph. Oh, wait, that's weird. I thought it was -1 when we did the calculation. Design requirements less than or equal to 4 and percentage overshoot less than or equal to 5%. Let me just check that design requirement. Settling time, that's why, less than 4, then enter. Okay, so now basically where dominant roots have to be. So we have to select a region within this white area. And so what I would suggest is choose your real axis, choose it to the left a little bit. So I'm going to choose -2, and I'm going to go up by 3. I notice make your imaginary part greater than your real part. That's like a general rule of thumb. It sort of works better. So I'm going to choose here -2, 3 for my S1. And so this is going to be the location where I'm going to choose S1 here. So pretend this is going to be -2, comma 3, and then my S1 conjugate would be right below at -2, -J3. And so that's going to be my S1 conjugate. I like to choose the imaginary part so that it's greater than the real part. And so let's now go back to our work here. So let's go back to the visualizer. And so here, what we have to do now is we chose our dominant roots. So that was step 2, is basically we need to determine the pole locations that give the desired transient response. And so what we're going to see is that in order to give the transient response, we chose S1 to equal -2 and then plus J3. And so now that we have that, number 3 basically is what we have to do is we're going to calculate the angle so S1 is on the root locus. And so we have to make that point now on our root locus here. And so what we have to do specifically is for that to happen, So this is looking at step 3. We're going to have to choose our angle GCS1. So that's going to be the angle of the compensator valued at S1 is going to equal, and then it's going to be 2R plus 1 pi, then minus the angle of the uncompensated system. Okay, so remember when we had our plot, we chose a good representation of it, I guess, would be the following. Where we know our uncompensated system, we have two poles at s equal to 0, okay? And so that's just our uncompensated system. And we chose our dominant roots to be at -2 and then J3. So here's our S1, our dominant root. And so what we're going to do here, basically, is we need to calculate the angle specifically. And so the angle between our uncompensated system and our dominant root, what is that going to be? And so remember, in order to determine the angle between this, so from our uncompensated system over this angle here, it's going to be tan inverse of, and then it's going to be our imaginary part 3 over how much distance we travel in the x-axis, which is -2. And so here we're going to have minus, and so then it's going to be, if we calculate this, tan inverse, and remember, this is a pole though. So because it's a pole, it's actually going to be a minus here in front because it's in the denominator. Remember your transfer function, poles are in the denominator, so when you calculate the angle of them, it's going to be minus. So minus tan inverse, and then the imaginary part is 3 all over, and then the real part is -2. And so that's for one pole. Remember, we have two poles. So it's going to be minus tan inverse, and then our other one is going to be 3 over -2 because we have two poles there. And so I'm going to choose my R to be -1 here. I'm going to choose -1 so that my angle is going to be within the range I want it to be. So you're going to see what I mean by that. But this would be negative. So if I have -2 plus 1, that's -1. So -1 times pi, that would be -180 if I'm just going to put this all in degrees. Now, tan inverse, if I do tan inverse 3 divided by -2, remember my angle should be in this region here. I get -56, so I need to add 180. And so I get 123.69. So plus 123.69 plus 123.69. That's what I'm going to get specifically for each of these. And then -180 degrees, and then plus 123, plus 123. So I'm going to get -180, and then plus, and then 2 times that answer. So I'm going to get 67.38 degrees. Okay, so that's for my angle of my compensator. So that S1 is on the root locus. And so what we're going to see here specifically is we calculated the angle. And then step number 4 is you're going to choose Z under S1 and calculate the angle then of the pole. So what we're going to see here is we're going to choose our Z to be right under S1. So we're going to let Z, it's going to equal here. If we do that, Z specifically will be -2. And so that's what we're going to see right here. It's going to equal -2. So it's right under that root locus. And so the dominant pole right here, we're going to choose our 0 so that our 0, let me do it in a different color, is right under our S1 point. And so the nice thing about that is that the angle here is going to be 90 degrees. So when the next step, you have to calculate, basically, we know our GC of S1, remember a compensator, you calculate the angle that, it's the angle, the 0 in the numerator, minus the angle of the pole in the denominator. And so if you solve for the pole, you're going to have the angle of the S1 plus C, and then minus the angle of the compensator. And so then our pole angle, this angle here, the 0 is 90 degrees because it's right under your dominant pole. So that angle is 90 degrees there, then minus. And then our angle of our compensator, we just calculated it to be 67.38 degrees. If you do the math on that, you're going to get 22.62 degrees for your angle of S1 plus P. So angle of S1 plus P. And remember, because we're designing phase lead to meet the criteria because it was not met on the step response of our graph, because it's a lead, in order to meet the transient response, our pole is going to be somewhere out here. And so we have to determine the angle of the pole. So looking at the angle of the pole here, our angle basically, how do we determine this? That's the main thing. And so we need to look, if we know this angle is 22.62 right here, we know this is 22.62 degrees. We know that our distance on the imaginary axis is 3 here, so this is 3. And we don't know the length here between, so this we're going to try and solve for. So I'm going to call this distance here just my x. We're going to try and determine our x. And so using trigonometry, if you use, we know opposite and we need to know our adjacent. So here, that would be tan of 22.62 degrees is going to equal opposite over adjacent. So my x length is going to equal tan of 22. Let's see, if we multiply this over the side, it'd be 3 over tan. At 22.62 degrees. And so if I do 3 divided by tangent of that angle, what I'm going to get is 7.2 for my x distance. So this is going to equal 7.2. But notice that your pole, that's only the distance from S1 to your pole. So it's only the distance here. Your pole location, you have to add how much. It's because there's 7.2 here. But remember, the S1 occurs at -2 plus J3. So you have to add that -2 to get the total distance along the real axis in order to determine your pole location. So this total distance here of your pole would actually be at -9.2 because this distance is 2 here plus a -2 and minus 7.2 gives you -9.2. And so just be careful because your S1 is offset by 2 from the real axis, so you have to add that. You calculated just the distance here, but you have to add the 2. And so we determined our pole location here basically. So S for our pole, it's equal to -9.2. That's the location. So we were able to determine our pole location. And then now step number 5, we need to choose K to satisfy this condition. So here what we're going to do for that is we're going to choose K so that our L of S, basically, L of S, if we have that here, is going to equal the magnitude, remember, because your open loop system is going to be the magnitude of your compensator. So that would be our K, and then the magnitude of S1 plus Z all over the magnitude of S1 plus P. And then the magnitude of your uncompensated system evaluated at S1 is equal to 1. Okay, so here, what we're going to do is we're going to plug in now. So let's just plug in what we know. So K is unknown right now. We don't know what K is equal to, but we do know how to find it specifically. So our S1, remember, we chose the dominant pole to be at -2 plus J3. And then our Z was located specifically at -2, correct? And then our pole, if our denominator, so we need to find the magnitude of that in the numerator. Then our pole, if we evaluate that, -2 plus J3, and then our pole occurred at -9.2. So we need to find the magnitude of that. And then we need to find the magnitude of the uncompensated system. Sorry, this is L1, S of 1. And so magnitude of the uncompensated system, remember, our uncompensated system is 1 over S1 squared. And so plugging in that S1 as -2 plus J3, and then squared, and then that's equal to, and then magnitude of 1 is just 1. So now we need to solve this. So we're going to get a -4 plus J3. And then in our denominator, we're going to have a -11.2 plus J3. And then here we're going to have 1 over, and then if you do the square of this, specifically what you're going to get is, here we would have 4, and then we would have minus J6, and then minus 9. And so is equal to 1. So then we have to find the magnitude of all this stuff here. So we just simplified and then multiplied by K. Okay, so now we need to find the square. If you have to find the magnitude, you need a 4 squared plus, and then 3 squared here. And then square root, and then in denominator, it's -11.2 squared plus, and then 3 squared. And then here it's multiplied all by K in front, and then 1 over, and then here we have -5 squared, and then plus -6 squared, and then take the square root of that because we have to find the, and then 1. So here what we have is we're going to have our square root of 4 squared plus 3 squared. And so that's just 5 here. So that's a nice number. Then all over our denominator, if we find the magnitude of that, take square root 11.2 squared plus, and then 3 squared. What I get is 11.595. And then here I have 1 over, and then if I have the square root of 5 squared plus, and then 6 squared, I have 7.810, and then K, and then it's equal to 1. Okay, so if I multiply this together, I'm going to have 1 divided by this, multiplied by 5 divided by 11.595. I get, then I do 1 divided by, move that over to the other side. K is equal to, and then here what I got specifically was 18.11. 1 or 112 if you want to be more exact. So that's what I got my K to be. And so now that I know that, the proposed compensator for step 6, GC of S, if we know it's K over S plus Z over S plus P. Okay, so our K was 18.112. Our Z, S plus, and then our Z we chose to be at -2. Remember, it's S minus a -2, and then S plus, and then 9.2 here. And so that's what I specifically got for my compensator. And now you have to evaluate the open loop system with your compensator. So let's do this in MATLAB. And so we're going to go back here. And so now we're going to pull open our control system designer with this specifics. So let me shut this session. And we're going to add our compensator. G of C is equal to 18.112 times S plus 2 divided by, and then we're going to have S plus 9.2. Okay. And so then we're going to do the control system designer of the open loop system. So it's going to be L1 times G of C. That's basically what we're going to have here. So if we launch control system designer 18.112 S plus 2 over S plus 9.2 of that, so it's going to pull up the control system designer, and we have to see if our design requirements were met, which were the settling time and percentage overshoot. And so now evaluating that, let's see if our dominant poles are there. So we should see S plus 2 and S plus 9.2. Our pole in 0 should be added. So we don't need the Bodhi editor, so I'm going to shut that one. And so what we see specifically here is we see we added the 0 and we added the pole. So that's our phase lead. Remember, the pole comes first. So that looks correct. now what we have to evaluate specifically, let's pull this figure over to the right. So let's add in our design requirements here. So new. Settling time has to be less than or equal to 4 seconds. Percentage overshoot is going to be less than or equal to 35%. Okay, so we know here what we have basically is we have to see if it's satisfied now within our actual step response. So we're going to have the rise time. Remember, you have to set the rise time less than the settling time, so MATLAB doesn't give you an error. And then percentage overshoot is 35%. And so see that we got close, but we didn't hit our design requirements exactly. So then what I would have done, basically, if I saw this, I would go back and then I would choose my dominant pole location. So notice that within here, I got close, but I didn't hit it. So it's better than the first graph. So for my phase lead, I have to then go back and reiterate. So we introduced the pole and zero compensator, which is great here. But I'm going to have to re-choose my dominant pole locations in order to satisfy those dominant those requirements because I did not meet them. I still had too much overshoot here. So this is a process where you would go back specifically. So on our graph here, instead of choosing -2 plus J3, I would have chosen a different point. And so you have to go back and then maybe I would have made the J a little larger. So I got closer to that edge point. So this is a reiteration where you evaluate and you would have to choose a new dominant root. And so we got close, but we didn't satisfy it. So, you know, but that's the step process of how you would make a phase lead compensator. So, you know. And so our next one, what we're going to do specifically is let's look at the phase lag system. And so for a phase lag compensator, what are the design requirements? What are the general steps, I guess, first? So if we have a phase lag compensator, how are we going to follow that? And so remember, for your phase lag compensator, it still comes in the form here. It's equal to K and then S plus Z over S plus P. And then your zero comes first before your pole. Okay. So step number one is basically what you need to do is you need to find the root locus of the uncompensated system. And so that's your L1 of S, which is equal to your G of S times H of S. And so this one basically here, what we do is we find it, the uncompensated system, the plot of the root locus. And then the next one is you determine the dominant root locations or the closed loop poles. So determine the closed loop for dominant pole locations. And so when I talk about this, this is S1 and S1 conjugate. On the root locus that give the desired transient response. And then after that, you need to find the corresponding loop gain, K naught. So this would be, so here, find the corresponding loop gain, K naught. And so at the desired poles. So MATLAB's going to tell you this, how much gain you need in order to get to those desired poles. So we're going to see that. You call that K naught. And then from there, you need to calculate the gain required to give you the steady state response because you use phase lag only for steady state response. So calculate gain required to give you the steady state response, or the desired steady state response. I'll just add that here. So that's what we call K of S. And then what we're going to do is we're going to pick Z, or choose Z, so that it is much smaller than omega n, which omega n is equal to the absolute value of your S1, your dominant pole. And so what you're going to do here specifically is you're going to see that your pole is going to equal your K naught times Z all over KS. So that's how you're going to solve for your pole. And then your next step, number 6, it's basically you're going to evaluate the compensator. So after you chose the 0, then you got the pole, and then you're going to evaluate your specific compensator. So your GC of S is going to equal your K naught of S plus Z over S plus P. So remember, K naught is the amount of gain you have in order to give you your desired pole locations, which are S1 and S1 conjugate. And so that's told by MATLAB. Then you calculate the gain required to give you the steady state. So that's called K best, the amount of gain to give you the steady state. You choose your Z, and then you find P using this formula. And then so you got your Z, your P, and your K naught. So then you evaluate the compensator. So let's look at an example where we have to design. And so for this example, we're going to follow the steps. So basically it says we're given the following system. We have our input RVS. It's going to go through to the summing block here. So we have a compensator. And then we have our GVS. And then it goes to the output C of S. Okay. And so here our GVS is going to equal 10 over S times S plus 5 multiplied by 1 over S plus 10, okay? So what we need to do here is the design so that, and what's going to tell us is settling time is less than or equal to 4 seconds. It's going to say percent overshoot is less than or equal to 20%. And it's going to say steady state error for a ramp input is less than or equal to 5%. Okay, so what I know from here is I'd be like, hey, my settling time needs to be less than or equal to 4 seconds. So 4 over zeta omega n needs to be less than or equal to 4. And so then that is literally just telling me zeta omega n has to be greater than or equal to, and then 1, negative zeta omega n, it has to be less than or equal to negative 1. Your percentage overshoot, it's basically just telling you that your zeta has to be greater than. Looking at the table, it's about 0.45. And so then if you calculate the angle of that, if you take the cosine inverse of 0.45, what we're going to get is like 63.26 about for angle. And then your steady state error, if it has to be less than 5%. So that's what we're going to have to determine here is how do we ensure that our steady state error is less than or equal to 5%. So remember, this is telling you that your steady state has to be less than or equal to 0.05. And remember, for a ramp, your steady state error is given by 1 over kV is less than or equal to 0.05. So this is basically just telling you if you move kV over to the other side, your kV is going to have to be greater than or equal to, and then 1 divided by 0.05 is 20. So that's just looking at what it tells you in the design requirements, what you have to meet. So here we know our transient response here. Basically, -1, our zeta here, it has to be less than or equal to -1. Our angle that we have to satisfy is about 60 degrees. And so here's what we have to meet in our design criteria for the transient response. And so let's plot the uncompensated system in MATLAB. Okay, so I'm gonna clear everything. And so my S is equal to transfer function of S. And then I'm gonna have my L1, my uncompensated system, is going to equal 10 divided by S times S plus 5 times, and then here we're going to have 1 divided by S plus 10. Okay, and then we're going to do control system designer of your uncompensated system L1. And so 10 divided by S times S plus 5 multiplied by 1 divided by S plus 10. Okay, cool. So we run this. Let me close the last one from the last session. I don't want to save that. Okay, so this is what I have here. And that looks about right. I have pull at 0, pull at -5, pull at -10. Okay, so from here, what we need to do is looking at our design requirements, I'm going to insert those. Settling time has to be less than 4 seconds. So let's enter that one. Oh, here it is. Settling time less than 4 seconds. And hit enter. Okay. And then I'm going to do my percentage overshoot is going to be less than or equal to, and then here it's 20 seconds. And then I'm going to add the same thing here, new design requirements. And then so our settling time has to be less than or equal to 4 seconds. So I need to make my rise time a little less than that. And then 20% overshoot here. Okay. So notice that our transient response, basically we're not hitting. The percent overshoot, yes, we're good. But the settling time, we're not fast enough. So that's the big thing that we would specifically notice here. And so this one, he would have to tell you that what we have here is when we're analyzing our root locus, because he wants us for this example just to use the phase lag. So we're going to look at our phase lag specifically here and how we can adjust this in order to meet our requirements. And so he wants us to choose the dominant pole locations in order to get the desired transient. And so if we move, notice that if you move these poles, see how it's going to cause my, what we get here is when we move these, we're actually able to satisfy what we want. So I don't want to be that high, but let's say if we're around here, that looks like we're pretty good in terms of being met, correct? Okay, so real quick, what you're going to notice here is it tells you at the bottom. So it's really important. It says your natural frequency is 3.01. It tells you your pole location at -1.79 plus 2.42. And how do you determine the gain? Well, the gain here is given by your specific, I believe if we look at here, if you click on this, your compensator, it tells you the gain at this point is 10.376. So that's how you're able to determine. So remember, our S, basically we had to choose the S1 and S1 prime. So let me put this graph, let me try putting it on the left-hand side for you guys. And then let me try putting the visualizer on the right-hand side so you can see what I'm writing down. So your step 2, we chose our dominant pole locations. So my S1 here, because these are my dominant poles, they're closer to the J omega axis. I literally just drag them for the phase lag. These are at -1.7 or 1.86. And then I have plus J 2.13. And then my natural frequency is 2.83. And then my gain at this point look at the bottom left, how it tells me the C. I clicked on C and it says the value is 9.0415. Okay, so that's my gain, so my K naught is equal to 9.0415. Okay, so from that, it gives me the desired transient response that I want. I satisfy it in the time domain, and I'm in the white hands. You need to be in the white here, and you need to get the desired transient response. So I got all that information here, and now we need to, this K naught here, that gives you the gain at the desired poles, and so we found our S1. The desired pole, S1 conjugate, is just the opposite J term, so you know that. And then step number 4, we need to determine K of S. And so in order to determine K of S, what we're going to have to do is remember your KB, your ramp. When we have to determine the ramp, recall that the velocity error constant is the following format. It's S times your GC of S times your G of S, which is your open loop system, times S, because it's velocity here. And so what we basically have for here is, if we plug in what we know, this would be limit as S goes to 0, and then it's going to be S times our GC of S. All we basically know right now is this is going to be GC S. We don't know our compensator, but our G of S we do know, which is 10 over S times S plus 5 times S plus 10. Okay, so what we're going to see happen here is the S will cancel with the S here. So that's what we're going to get. And then we're going to have, if we plug in 0, you're going to get your GC of 0 times 10 over 50. And this is what your KV is equal to, and that is specifically your KV is equal to 10 over 50 is 1 over 5, or 0.2, GC is 0. And if you recall, from up above, your KV must be greater than or equal to 20. So here, this must be greater than or equal to 20. Your KV must be greater than or equal to 20. And so solving for GC of 0, you're going to particularly get that your GC of 0 is going to be greater than or equal to, divide by 0.2, you're going to get 100 here. And so when you get GC of 0, once you get GC of 0, this is known as your steady state gain that you need to have. So your steady state gain here, that is determined by once you isolate GC of 0. So just be aware that this is actually your K of S right here when you get GC of 0 by itself. Now, the 5th step is you need to choose Z so it's much smaller than omega n. So we're going to let Z, our omega n from MATLAB was 2.83. The value Z he put in the notes is 0.05. I just always use that because it tends to be less than our natural frequency. And so then the next one is we need to determine the pole location based on our parameters, K naught, then Z all over KS, which are K naught we determined to be 9.0415. Our 0 we determined to be at 0.05. We just chose that one. And then our KS was 100. Now, knowing this information, what I'm going to do is plugging it in. I get 9.0415 times 0.05 divided by 100. And that I get my pole to equal 0.0045. Notice, my 0 comes before my pole, which is the phase lag compensator, so that makes sense. And so my compensator is going to equal K naught S plus Z over S plus P, plugging in what we know for our K naught. For a gain, we had 9.0415 multiplied by our 0, which is going to be, so S plus our 0 is 0.05 all over, and then it's going to be S plus, and our pole was 0.0045. Okay, so that's my GC of S. So now I'm going to evaluate the controller. So I'm going to go back to my MATLAB. I'm going to close this because this is not with my controller. So looking back at my MATLAB code here, I don't want to save that other session, so I'm going to close that one. Here, we're going to have our GC is equal to, and this is 9.0415 times S plus, and then here we're going to have 0.05 divided by, and then S plus, and we're going to have 0.0045. And then we need to do control system designer of the open loop system. So it's going to be L1 times GC here. And so 9.0415 times S plus 0.05 over S plus 0.0045. Okay. Now that we have that, when we pull up the control system designer, we just have to ensure that our design requirements are met here. So I'm going to shut the Bodhi editor because we don't need that. And so now we're going to pull this open. Going to put this on the right-hand side here. Let me try. Yeah. So remember our settling time, you need to add that back in. So it's a little bit reiterated. Has to be less than 4 seconds. Then your percent overshoot had to be less than 30 or 20% for this example. Okay, so notice these are my dominant poles and they're now on the root locus, right? These pink dots here, those are the ones I chose. Those were S1 and S1 prime. And now my design requirements for this graph here on the right, my rise time, I set it as 3. My settling time was 4 seconds. I have to make my rise time less, and my percent overshoot was 20. Notice that it was met. So I properly designed the phase lag controller. Let's go. That's would show you that, hey, I met my requirements. My S1 and S1 conjugate are on the root locus. And so I did this. So there you go. That's how you design a phase lag. So now let's, we saw how to design a phase lag controller. And basically, now that we saw that, what you can do is sometimes you might need to have both a phase lead and the phase lag because you have to meet your transient response and you have to meet your steady state response. So basically, if you see a steady state error that you have to find, you know you need a phase lag. If you see a transient response, you're probably going to have to use a phase lead. And so just be aware of that. So the first step, if you were to be given a phase lead lag, if you have to design, first you would so if you have to do a phase lead lag compensator, so you have to do both, just know that it is very similar to what we talked about already, where the first step, you just have to evaluate the uncompensated system. So this would be where you look at MATLAB, so evaluate the uncompensated system, L1 of S in MATLAB, and then you would then you need to design the phase lead compensator to meet the transient specifications. And so design your phase lead compensator. And that's where you do your calculations, to get your design requirements. Compensator to get your transient response specifications. And then after you do that, so remember, this is where you would have to make sure that your compensator, it's K times S plus Z over S plus P. Then you would evaluate the compensator. After you design the phase lead, you evaluate the compensator and you see, hey, do I need to add in anything else? If you notice that the steady state error is really bad, then that's when you have to add in a phase lag compensator. So then this is where you design the phase lag compensator. And after you design the phase lag compensator, basically remember your phase lag, you're going to have your GC of S is going to equal, so this is GC1, this is GC2, S plus Z2, because these were your first, and then S plus P2. And then you would evaluate the lead lag compensator and make changes as necessary. So you just evaluate then. So you first design, literally what this is telling you is just first design a phase lead, then design a phase lag if your requirements are still not met. But he'll probably specify which one, I would hope, on the exam, because he probably wants to see if he can do both. So he'd probably make one problem where you design one and the other where you design the other one. Okay, so that's pretty much it for phase lead lag compensators. So now that we talked about that, let's get into PID controllers. So what a PID controller is. This lecture, he skipped a bunch, so I don't think it will be really examined on, so I'm just going to go over the basis. K of S is equal to KP plus KD of S plus KI over S, okay? So this is the proportional part, this is the derivative part, and this is the integral part. And so what we need to know is this is based on, the proportional is based on the present time. It's just proportional to the amount of gain that you have. This is like proactive, your derivative, because it's taking it like at the next time step, it's evaluating what it should be, because remember, derivatives between 2 points. And then your integral is sort of like reactive. It's looking at like the past, taking all like the accumulation over the past time. And so what we're going to know is that this is going to make our system, though, one step higher, since it's going to follow a step input. So there's going to be 0 steady state error because we have a step here. So that's the important thing. Just notice with the integral, it's going to diminish our steady state error because it's a 1 over S. So it's going to be like a step input. So when you tune KP, KD, and KI, that's known as PID tuning. And so what we're going to notice is that there's 3 main factors. So if we look at our KP, if you increase KP, so basically if I'm talking about the percentage overshoot here, the settling time, and the steady state error, what we're going to see here is that when we increase KP, what we're going to get is we're going to have an increase in percentage overshoot. We're going to have no impact really like on the settling time, but we're going to have a decrease in steady state error. And then if we increase KI here, so this is our integral. So if we increase KI, what we're going to notice is that this adds a pole at the origin, correct? There's a pole at the origin here. And so it's going to increase our percentage overshoot because now we have a pole that's at the origin. So what we're going to see is it's going to make our system a little more unstable. So more overshoot, we're going to have a higher settling time, and we're going to have those 0 steady state error because it introduces a 1 over S. So it eliminates the steady state error. Then our KD, what we're going to notice is this is a 0, right? Our KD is introducing a 0, not a pole. So 0, remember, pulls the root locus to the left. So 0 at the origin is going to pull the root locus left. So it's going to give us a faster transient response. And so it's actually going to do the opposite effect where it's going to decrease our percentage overshoot, decrease our settling time, but it doesn't have impact upon the steady state error because it's not it's the same input. It doesn't have like a 1 over S or 1 over S squared. It's not like a step, ramp, or parabola input. So it doesn't have any impact. And so what we're basically going to notice within here is then you just tune all of them to get what you want. But he really just focused on towards the end what you should know. So let's look at the pre-filter systems and let's look at the deadbeat response because those were the only 2 that were covered in depth. And so now we're going to get the pre-filter. And so the pre-filter, how this one works, is that the pre-filter comes beforehand. So we have our R of S here. And then we go through our pre-filter, which is GP of S. So this is the pre-filter. And then it's going to go through a summing block here. Then we're going to go through our compensator. Then we're going to go through our process, and then we're going to go to our output. So our output C of S here. And so what we have to do within here is this pre-filter, it's going to mitigate the effect of closed loop zeros. And so it's going to improve our system performance. So the main thing of a pre-filter is it eliminates closed loop zeros, because notice it's outside of the closed loop system. Because here's our closed loop, it's outside of it. So it's going to eliminate closed loop zeros. And so what we're going to notice is you're generally in the format, if you have to do a pole zero cancellation, it's going to have a pole which is going to match the zero in the denominator, so cancel the zero of the closed loop system. So it's going to have a pole to cancel the zero. And we need to make sure the DC gain is 1. So we're going to have P over P, because at S equal to 0, it's going to be P over P, so it's 1. So we make sure that the DC gain equals 1 of our pre-filter. So DC gain GP of 0 is equal to 1, so it does not affect the DC gain of the system. And so what we'd have to do for a pre-filter system, basically, if we have, let's say that our transfer function, if you gave us our transfer function and it was equal to, and we have 67.5, we have S plus 1.2 all over S plus 11 times S plus 1.63 times S squared plus 3.37S plus 4.530. Okay, so we notice we have a 0 in the numerator, and we're not meeting our system conditions, let's say. So if we're not meeting our system conditions, we can use a pre-filter. And so this pre-filter, if we choose basically our pre-filter to be GP of S is equal to, if we want to cancel the 0 here, it would be 1.2 all over S plus 1.2. So the DC gain would be 0, and we'd eliminate that 0, so we'd have a pole 0 cancellation. And so that will give you a better transient response, what you're going to see. So that means that less percentage overshoot and a smaller settling time. And so that's how a pre-filter works. Just eliminate zeros to give you a better transient response. So if you ask about that, you know how to do it. Okay, now the next one is going to be talking about the deadbeat response. So the deadbeat response, basically, it's going to be minimal percentage overshoot. So some things about it is the steady state error equals 0. It's a fast response. It's going to be a percentage overshoot less than 2%, and a percentage undershoot less than 2%. Oh, oops, undershoot. Okay. And so what we're going to see here basically is your graph is literally going to look like something like that. It's going to just get to it, not have undershoot, not have overshoot, and it's going to be really fast in terms of its settling time. And so that's what a deadbeat response graph looks like. And so let's say, for instance, if we had a transfer function given to us, it's equal to omega n to the power 3, so it's a third order transfer function. S to the 3 plus, and then alpha omega n S squared plus beta omega n squared S plus omega n cubed. Okay, so first things first is we're going to normalize this. And so if we normalize this, what we're going to get is we're going to get T of S is equal to 1 over, because you divide by omega n cubed. And so we're going to have S over omega n cubed plus, and then this would be theta, and then S over omega n squared, and then plus beta, and then it's going to be S over omega n, and then plus 1. So that is normalizing it. And so if we normalize it, you're going to get a table. And the table is going to tell you, based on the system that you have, what are your coefficients, basically, if you have a normalized system. So you have to normalize your transfer function in order to use the deadbeat response. And so the table for the deadbeat response is given by the following here. So all these values are normalized. So if you have a third order system, this would be your alpha, this would be your beta. And so those are your coefficients that would go here, your alpha and your beta up above. You would plug in these 1.9, 2.2. And so let's look at specifically how, and then this would be like your settling time and your rise time. So it gives you all these if you have a normalized system. So let's look at an example of how we would apply this. And so here, what we would specifically do is, let's say that we have the following, where we have R of S, and then it's going to go to our system, which is going to be, so it goes into our pre-filter, and then we have a compensator, here, plus and then minus, then goes into a compensator, GC of S, and then it goes into a process, G of S, then it's going to produce an output C of S. This goes backwards, and so our compensator, and then our system, okay? And so what we need to do now is our G of S, they tell us, is equal to 1 over S times S plus 1. Our GC of S is equal to K times S plus Z over S plus P. And then our GP of S is equal to Z over S plus C. So it says design a deadbeat controller to achieve a settling time less than 2 seconds. So we want a deadbeat controller with basically a settling time T of S less than 2 seconds. Okay. So what we have to do is, what I suggest is you find the transfer function of this system, because we have a pre-filter. The pre-filter is going to cancel 0 in here. So let's evaluate this specifically and look what we're going to have. So if we find a transfer function, our T of S is going to equal, and so if you do G C of S times G of S all over 1 plus GC of S, G of S, what you're going to get is you're going to get K times S plus Z, and then it's going to be all over S to the 3 plus, and then P plus 1 S squared plus S P plus K, sorry, times S plus, or yeah, plus KZ. Okay, so that's our transfer function within here. But remember, you need to multiply that by the pre-filter. And so this is just our transfer function, but our entire transfer function here, what we're going to have specifically is we need to multiply by that pre-filter, which is given to us by Z over S plus C here. And so we're going to have our pre-filter system, so then Z over S plus C multiplied by this. Interesting. I think he might have made Z over S plus Z. Okay, yeah, S over S plus Z. He made an error in the notes, but here, just correcting it. Then K times S plus Z all over, and then it's going to be an S to the power 3 plus, and then P plus 1 S squared, and then plus P plus K S plus KZ. Okay, so what we need to do here is we're going to notice the 0 from our system is going to cancel with the pole here. Oh, this was a Z in the numerator, my bad. So we're going to be left with the transfer function KZ all over S cubed plus P plus 1 S squared. plus P plus KS plus KZ. Okay, so what we have to do here is we notice we have a third order transfer function, correct? We evaluated the entire transfer function in the system from input to output. And so this is the third order. So what we need to determine is we're going to have it normalized in order to use the response, correct? So basically for a system, what we're going to do here is our normalized response. What we're going to have is this is going to particularly looking at what we have here. We have the s cubed right here, and we have the s cubed right here. This term must be the omega n cubed, so this term must be the omega n cubed. This term must be the alpha omega n here, alpha omega n. This is the beta omega n matching up here, beta omega n squared. And so what we're going to have here is if we just look at those, our omega n cubed is equal to then KZ, and then we have our alpha omega n is equal to P plus 1, and then we're going to have beta omega n squared is equal to P plus K, and then what we do is if we try and get this into the format we want, noticing our deadbeat response table, we have a third order right here. So that's a third order. Looking at we have specifically here is for a third order system, notice that we have these coefficients right here, 1.9, 2.2 for beta. And in order to achieve our settling time, right here for the normalized, it's 4.04. So this is T of S, and this is the normalized table, so it's times omega n. So in order to get a settling time of 2, basically, if we plug in, so we saw our settling time here was 4.04 for a third order system. So from the table, we were able to see that omega n T of S is equal to 4.04 because this is the normalized settling time from the table. So if we have our T of S is equal to 2 seconds, it's going to be omega n is equal to 4.04 divided by 2, which that specifically is going to be 2.02 for omega n. And now, if we know our omega n is equal to 2.2, then we know omega n cubed here basically is just going to be 2.02 cubed. And so then that'd be 8.24 for kz. So this would equal here 8.24. And then p plus 1, if we know our omega n, and we know the alpha from the table is 1.9, because this is from the table, it's 1.9, and we know this, we just solve for it 2.02, you're going to be able to determine P plus 1 is equal to, and then that's 3.84. Then beta from the table for the deadbeat response is going to be 2.2. And then your omega n, we know this is going to be 2.02, and then square it. When you solve that, you're going to get P plus K is equal to 8.98. So what we're able to determine from here then is now you can plug those in order to solve for your P, your K, and your Z term. So you're going to find out basically if your KZ is equal to 8.24. If you're able to then specifically solve for all these, you're going to be able to find that your pole is equal to 2.84, is P plus 1 is equal to 3.84 minus 1, you get the pole equal to 2.84. If you know your pole now, then your pole plus the K is equal to 8.98. You can solve for K. So K would be equal to 6.14. And then your Z, if you know your K, you just solve for your Z here, you're going to get Z is equal to 1.34. So you're able to solve for your K, your P, and your Z. And so that's basically how you use the deadbeat response in order to solve for those parameters. And then knowing those, you can just plug it now into your, so we know our controller that we need to have for the deadbeat response here. And so that would give us the specific one because we know the K, we know the 0, and we know the pole. And so this would be our deadbeat response. So what we did is we know for transfer function, we found the transfer function with the pre-filter, and then we looked at the table. This is the omega n cubed, if we remember from here for a third order system. This term right here is the alpha omega n, so alpha omega n, the beta omega n squared, and then the omega n cubed, and then literally we just matched the coefficients with the table after we solve for the settling time to get our omega n value. And so we solve for omega n, then you can solve for your z, your p, and your k, and that gives you the deadbeat controller. Now that we talked about that, that's pretty much what you need to know for that section. Now we're going to look at the frequency response. So this is going to be all the Bode plots. So that was basically the first half of it. Let's just take a 2-minute break real quick. So I'm going to just pause the recording. So let's start with the frequency response. So the frequency response, let's get into it. So for the frequency response, you often are used to seeing your GVS, which is like your open loop transfer function, oftentimes, where you have your Y of S over your X of S, your input. So in order to find the frequency response, you substitute in for S, J omega. So literally you just plug in for S, J omega. Just pure imaginary, because remember, S has the real part sigma. S is equal to sigma plus J omega. If you don't have sigma, if that's 0, you're just going to be left with J omega. So this would be Y of J omega all over X J omega. And so what you'd have to determine for the frequency response is oftentimes they ask about the magnitude and the phase. If they ask about the magnitude and phase, we know for G of S that is literally just the magnitude of G of S is equal to the magnitude of the numerator over the magnitude of the denominator. And then for the phase, it's going to be angle of G of S is equal to the angle of the numerator minus the angle denominator. Okay. And so then for your magnitude here, G of J omega is going to be equal to Y of J omega divided by, and then the magnitude of X of J omega. And then your angle G J omega is equal to angle of Y J omega minus the angle of X J omega. And so that's our frequency response. And so now that we got that, we're going to look at specifically Bode plots and how we're going to analyze that, and also how we can determine those. So we're going to do a lot of these examples where, let's just dive into it. We have to plot the Bode plot. So best way to learn Bode plots is doing examples with it. So G of S is equal to 1 over S plus 1. Okay, so it says determine the magnitude and phase frequency responses here. So immediately, if you're looking at this, if he wants you to actually write out the equation, if he said magnitude and phase frequency response, if he wanted you to derive those equations, then what you do is we know that you just literally plug in for G of S, you plug in G J omega. So for S, J omega. So it'd be 1 over J omega plus 1. To find the magnitude of that, G of J omega is equal magnitude of the numerator and the magnitude of denominator, which would be 1 squared, the real part squared, plus the imaginary part squared. And so this would equal 1 over, and then omega squared plus 1. Take the square root of that. Now, in order to determine the phase, you do the angle G J omega is equal to angle numerator, so angle of 1, minus the angle of the denominator. So tan inverse of the imaginary part over the real part. And so that would be angle of 1 on your unit circle. Remember, 1 is literally just here. So it's 0. So 0 degrees minus, and then tan inverse of omega. So we'd have to determine that. So tan inverse of omega. And so your response would just be minus tan inverse and then of omega. That is your magnitude, or sorry, your phase. And this is your magnitude up here. So those would be your magnitude and your phase. So in order to determine, if he asks you for the Bode plot, okay, Bode plots, we notice here we have one pole. So we have one pole in the pole. This is normalized. And so a lot of times you have to look at a system and determine if it's normalized or not, because that's going to determine where your pole actually starts to occur in the Bode plot. So we'll look at a few more examples with this, so don't worry. But what we're going to see is that if we have omega here, so right now, what we're going to have basically is we start at 0 because we have no contribution by any constant. It's 20 log of 1, because if you evaluate this numerator, it's going to be 20 log of 1. And then in our denominator here, you're going to notice that it's just going to occur specifically at so minus 20 log, and then you would have it written so that it would be the magnitude, so which is omega squared plus 1. Because literally we look at our magnitude response if you wrote the equation, because on your Bode plot, on the magnitude axis, you plot 20 log and then of g j omega. And so that's equal to 20 log of the numerator minus 20 log of your denominator. And so what we're going to see here specifically, 20 log of 1 is just 0. So it's going to start out as 0. So here we're going to start as 0 dB. This is in decibels, so you know. And what's going to happen is specifically at 10 to the 0, which is just equal to 1. So you know, because this is normalized, so it's just 1. It's so what we're going to see is it's going to decrease with a slope of negative 20 dB. And so it's going to go negative 20 dB. So here, let's say if this is specifically our negative 20 dB point here, and this is our 10 to the power 1, because for 1 decade, it goes negative 20. So that's the pole that contributes. Now, if we have to look at the phase plot, our phase plot specifically is going to be a little bit different. So this was our 20 log of gj omega. The phase plot is just going to be angle g j omega. So for the phase, we're going to notice that our pole contributes basically 1 decade before and 1 decade after, and it's going to have a negative 45-degree slope. And so originally the phase is just 0 degrees, and so it's going to start at 0 degrees. So if this is 0 degrees, and then we're going to have negative 45 degrees, and then we're going to have negative 90 degrees, okay? And so it's going to start out at 0, and 1 decade before would be 10 to the negative 1, so before the pole occurs, at the pole location, and then 1 decade after. And so 1 decade before, it's going to start declining, negative 45 degrees, and then 1 decade after, it's going to then make it, and then the full 90, and then go to just stay constant. So a pole contributes 90 degrees. 45 degrees, a negative 45 degrees, 1 decade before, and negative 45 degrees, 1 decade after. And so that's the contribution by the pole. So that's the phase plot. It has negative 45 degrees per decade. So that's just the main thing to take into account. So what we're going to do is we're going to look at another example where we're going to have to draw the Bode plot. So if we have the following system, g of s is equal to, and then we have 1 over s times s plus 1. So it says determine the magnitude and phase responses. So magnitude and phase frequency response. So magnitude and phase frequency response. So what we're going to have here is, if you're told the frequency response, you know, for s, just plug in j omega. And so that's what we get here, is for the magnitude of g j omega, it's going to equal 1 over, so magnitude of 1 is just 1. And then we're going to have j omega here, and then you're going to have j omega plus 1 here. If we have to take the magnitude of each of these terms specifically, we're going to get 1 over, and then it's going to be omega squared square root of that. So that's just omega. And then square root of your real part squared plus your imaginary part squared. And so this is going to equal 1 over omega, and then square root of omega squared plus 1. Okay, so that's your magnitude. Your phase is going to be angle of g j omega, which is going to equal in your numerator minus the angle of your denominator. So the angle of your numerator, angle of just 1 is going to be 0 degrees. And then angle of your j omega in the denominator. So it's going to be minus and then tan inverse. And then it's just omega, your imaginary over your real part. And then the other one's going to be minus angle of tan inverse. And then it's going to be omega over 1, the imaginary over real part of this one right here. And so what we're going to notice here is you're going to have minus basically tan inverse of omega minus tan inverse of, let's see here. Oh, notice this is pure imaginary. My bad. Notice it's pure imaginary here, this omega term. So because it's pure imaginary, that's a big thing. We need to realize that this, notice it has no real part. It's just pure imaginary. So remember, pure imaginary is just 90 degrees. And so it's going to be minus 90 degrees here. And so you're going to have basically here, negative 90 degrees, and then minus tan inverse of omega. And so now if we're to plot this basically on a Bode plot. So if he says Bode plot of this, what we're going to do is, remember, for the magnitude plot, it's 20 log of gj omega. So looking what we have here in our numerator, it's 20 log of 1, which is just 0 minus 20 log. And then what do we have in our denominator? We have in omega, then minus 20 log, and then we have square root of omega squared plus 1. Okay, so what this is going to be, this term will just go to 0, so we know. So it looks like this one's going to specifically occur. The thing about if you have like a S, notice that this is just like a pole at the origin. If you have a pole at the origin, it contributes negative 20D per decade, and it's going to intercept with omega is equal to 1, so you know. So what we're going to see in our Bode plot is basically this one. If we have our omega here, and we're going to have 10 to the 0 here. So this first one, let me just show you guys what this one looks like. So for this part right here, because this is the one, this is just the pure pole at the origin. So this is a pole at the origin, this minus 20 log omega, it's going to contribute negative 20 dB, and it's going to intercept specifically with omega is equal to 1. And so that's, if you think about it, negative 20 log of 1, it intercepts 0 dB. So that makes sense. It's going to intercept this 0 dB point, and it has a slope of negative 20. So here, I'm just going to draw this. So we know this is negative 20 dB per decade. Now, my other one here, it's going to occur at omega is equal to 1. And so this one, if we draw it out, this one occurs at omega is equal to 1. So before it's just 0 dB, and then it gets a slope of negative 20 dB per decade. Notice that this is not a pole at the origin. So that's why it doesn't have originally a starting point in negative 20 dB per decade. It starts actually at that corner, that cutoff frequency. And so what we're going to see here is if you sum the two together, summing what we have is basically if you add the two plots, you're going to get the following response here. And so this is going to be our omega. And so it's going to be negative 20 dB per decade here. So negative 20 dB per decade, because 0 plus negative 20 dB, you're going to add these two together and you're going to see, okay, that's the one line I have. And then if you add negative 20 dB with negative 20 dB, you're going to get a negative 40 dB, just so you know. So that would be your resulting plot from it. So that's what you're going to have here. And then this would be the intercept of 10 to 0, which is just omega equals 1, because that's the cutoff frequency. Now, we're going to have to graph the phase plot. So looking at our phase plot, so that was just our magnitude plot. So you'd label here 20 log of g, j, omega. And now if we have to do phase, that's angle GJ omega. And so what we're going to notice here on our phase plot is specifically, we're going to have it starting at negative 90 degrees. So here, this one's going to contribute a negative 90. This pole, because it's pure imaginary, so it's negative 90. And then the other one's going to be 1 decade before and 1 decade after omega is equal to 1. And so for the omega here at 10 to the 0, which is 1, it's going to be negative 45 dB 1 decade before, so 10 to negative 1, then say if this is 10 to the power of 1, negative 45 degrees. So this one would be negative 45, and then another negative 45 here, and then that's it, because each pole contributes negative 90 total. So this would be 0 degrees, negative 45 degrees. And so at that cutoff frequency of 1, it's already halfway, and then it contributes another negative 45. And so if you superposition both of these, what you're going to get is the superposition principle. You're going to notice that your phase plot is going to be here. It's going to be 10 to negative 1, 10 to the 0, and 10 to the 1. And so here we're going to get 90, 0, so it's negative 90. So the resulting one here, I'm just going to draw it here in black, negative 135, and then negative 180 degrees. And so we should expect it, because we have two poles, we should expect it to go to negative 180 at the end. And so here it's going to be starting at 90, and then we're going to start decreasing negative 45 degrees with that, then another negative 45. And that's what our plot will look like for the phase, because we use the superposition of both of them. Okay, now that we saw that, we're going to look at a third example on Bode plots, which is very important, I think, to know. So this one is going to be our G of S. It's going to equal, and then here we're going to have our K times S plus Z1 times S plus Z2 all over S plus P1 all over S plus P2. And then there's going to be an S to the M term here. So that's going to be poles at the origin. What we're going to see here specifically is we're going to have poles repeated at the origin. Okay, so what we need to do here is basically we need to find the magnitude and phase frequency response. It's going to ask us for that. So magnitude and phase frequency response. Okay, so let's try and determine that from here. So the frequency response, if we just look at it, G, J, omega is equal to K, and then it's going to be J omega plus Z1 times J omega plus Z2 all over, and then J omega to the power of M times J omega plus P1 times J omega plus P2. And then here, what we're going to have is the magnitude. If we take the magnitude of this, we're going to have it equal to K, and then the square root of, and then it's going to be Z1 squared, the real part squared, plus the imaginary part squared, and then square root of, and then it's going to be real part squared plus imaginary part squared all over. And then it's going to be down here, if we have to take the absolute value of this is just going to be omega to the power of M, because if you square this and take the square root of it, it would just literally be, if you square this, take square root, it's just going to be your, remember, imaginary part, square it, then take square root, it's just going to be omega to the M. And then if you take this one, it's going to be omega squared plus, and then your P1 squared, so your real part and your imaginary part, square them, sum them together, and then take square root. Then here it's going to be your imaginary part squared plus your real part squared, and then take square root. So now if you work this all out, you're literally just going to get, it's going to equal. So notice here, the big thing though, we need to make sure K, because it can be negative, so that's why we include an absolute value here. Just because we're unsure if it's positive or negative, we want to make sure when you take the square and take square root that you make sure it's positive. So that's why we include this here. And then just simplifying this, what we'd actually have here is omega squared plus Z1 squared, and then square root. And then it's going to be omega squared plus Z2 squared. And then all over, and then here we're going to have omega M, and then square root of omega squared plus P1 squared. and then square root of omega squared plus p2 squared. Okay, so that looks good right now. A big thing though, which is gonna make this a little bit easier, I would say. So this is one approach you can do, which isn't wrong per se, but I think it's easier if you normalize this equation first, because if you normalize, it's gonna make your mathematics a lot nicer, so that when you plot it, it all starts from like 0 to b and 0 degrees. So it's a nice plot. So I consider normalize it first. So you got gj omega is equal to k. And then what you're going to do here, in order to normalize this, you're going to do, specifically, you'll have your j all over omega divided by z1 plus 1. So if we take out a z1, if we divide this by z1, what we're going to have here in front is actually our z1's going to come to a front here. So I have a, yeah. So your z1's going to come out here. So you take out a z1, so it would be k times z1. And then here it would be j times omega divided by z2 plus 1. So this would be your z1, then your z2. And then in your denominator, if you normalize your denominator, you want to just get a plus 1 and a plus 1 here. So you're going to take out a p1 and a p2. And so what you're going to have here specifically is you're going to take out the p1 and the p2. So you're still going to have your j omega to the power of m. And then you're going to have j omega divided by p1 plus 1. And then j omega divided by p2 plus 1. Okay. So normalize first. That's going to save you a lot of math work. So when you do this, 20 log, if we have to find the magnitude response of j omega, what we're going to get is 20 log. And then here, what we're going to have specifically is it's going to be the absolute value k z1 z2 all over p1 p2. And then we're going to have plus 20 log, and then it's going to be the square root of, and then if you look at your real part, it's just 1 squared, so it would just be 1. And then if you look at your imaginary part, it'd be omega divided by z1 squared. So here it'd be omega divided by z1 squared plus, and then 1. And then in your numerator, you also have plus 20 log, and then it's going to be square root of your, and then here it's going to be omega divided by z2 squared plus 1 squared, which is just 1. And then here, we're going to have specifically, notice this one, when you do take, this would be minus 20. Then remember, properties of log, the m, the exponent will drop to the front. So it's going to be m log, and then it's going to be the absolute value. This is going to be omega, basically. And then your next one is going to be minus 20 log, because this is a pole, so that's why it's minus 20 log. And it's going to be square root of omega divided by p1 squared plus 1. And then the next one's going to be minus 20 log. And it's going to be a square root of omega divided by p2 squared plus 1. Okay. So here we got the entire magnitude plot. So if we're to plot this, what it's going to look like is it's going to be a superposition. So we notice we have 2 zeros, we have 2 poles, and we have like this constant term. Sorry, we have multiple poles. We don't know how many, but we have a constant here. So what's going to look like is the following. Okay, so right here, this is going to be 20 log of a constant, this term. So I'm going to go in order. So this term right here is going to be 20 log of some constant number. So let's just say that constant is positive. So it's going to be something like this by that term there. Now our next one here is going to be 0. So it's going to be a slope of positive 20. And remember, it starts at your z1. And so your z1 here, it's going to be specifically, it's going to be where it starts. So say if your z1's here, this is where you're going to specifically start with a slope of 20 dB per decade. Okay, now our next one is going to be another 0, which starts at z2. So I'm going to have this starting at z2. Let's say it's over here. So it's going to be 0 dB until you get to Z2. It's going to be 20 dB per decade. And then this one right here, this is multiple repeated poles, negative 20 m log of omega. So this one, what it's going to look like is it's a slope of negative 20. Remember how it's right at, it's a pole at the origin. So it intercepts 1 when omega is equal to 1. So at our 10 to the 0, because if this is on log scale, or I'll just make it 1 for now. So 10 to the 0 is equal to 1. So just know that. It's going to intercept with a slope of negative 20 m dB per decade. Because negative 20 m, so say if you have 2 poles at the origin, it'd be negative 40 dB per decade, and it intercepts 1. Now our next one here is going to be our pole. So our pole is going to be negative 20 dB per decade, and it occurs at P1. So here at P1, it's going to be negative 20 dB per decade. So here it's going to be negative 20 dB per decade. And then our next one is going to be a pole that occurs at P2. Let's just say that P2 occurs right here. It's going to be negative 20 dB per decade. So this one's going to go all the way up to P2. Going to be negative 20 dB per decade. And so this will be right here. It's going to be negative 20 dB per decade. Okay. Now after you plot all this, you're going to have to do the superposition of all them. So you would just add all these together like we saw originally. And that's pretty much what you will get here. And then your next one's going to focus on the phase. So the phase of G, J, omega, what is that going to be? Well, it's dependent upon, if we have to determine the phase from here, we have to do the, this is going to be a constant, right? This number here is going to be constant, K, Z1, Z2, P1, P2. So if it's positive, it's 0 degrees. But if it's negative, it's 180 degrees. And so this would be if it's greater than or equal to 0, if it's a positive number, but if it's less than 0, if it's a negative number, that constant, then it's going to be 180 degrees. And then plus, and then we have tan inverse, because we're looking at our 0 point, then it's omega divided by Z1 divided by 1, so that's just tan inverse of omega divided by Z1, plus tan inverse, and then it's going to be omega divided by Z2. And then our poles in the denominator, we're going to have minus, and then it's going to be how many poles we have. So that would be m times 90 degrees, because they're purely imaginary. So 90 degrees times m. It's in the denominator because it's repeated poles, so that's why the minus sign. And how many we have is m times 90 degrees. Next one is going to be minus, and then it's going to be tan inverse of omega divided by P1, and then minus tan inverse, and then it's going to be omega divided by P2. So that's how you would do that plot here specifically. And so if you need to put this on your Bodhi plot, what we're going to notice is it's going to be 0 or 180, dependent upon which one it is here. So this term, it really depends on if this value right here is a positive or negative number. And then, so this contribution, I'm just going to say for now, if you look at this and say it was a positive number, if he gave you, it would just be here. So it'd be 0. Now we need to look at the second term. Remember, it's 1 decade before and 1 decade after this one. So let's say if Z1 is here and this is like 1 decade before over here, and then 1 decade after, and then it goes. So that would be by 0, would be up to 90 degrees at the end. So it would occur 1 decade before and 1 decade after. This Z2 here, it'd be 1 decade before and 1 decade after. And so here it'd be 1 decade before and 1 decade after this. So it'd be like about here-ish. And then if we look at our poles and denominator, this one is negative m times 90. So how many we have here? It would be negative m times 90. So it might be negative 180, negative 270, depending on what the value of m is. Now here, we need to determine right here. This one is going to be the pole. It would be 1 decade before and 1 decade after. So around here, 1 decade before and 1 decade after. So it would go about, let's say here, to negative 90 degrees. And then the P2 would be 1 decade before and 1 decade after. So this one, it would be 1 decade before is around here. And look like this. Then you use superposition and you add all of them together. So that's pretty much it. How you would plot that. So that's a really good example. And just make sure you normalize. That's the big thing. Normalize these. So you get it so that it's +1 for the zeros and +1 for the poles. That's the big trick in order to solve these, so you know. Okay, now that we determined that, what we need to examine basically now is, this is going to be a little conceptual because you might ask about it. This is leading into the next lecture note, so I think it's important that we talk about this so that you do well on that one. But this one's basically talking about our bandwidth of open loop versus closed loop systems. And so what we're going to notice is for an open loop system, so let's look at open loop versus closed loop. So for an open loop system, if we have our input and then it goes through a transfer function, and our first order transfer functions in this format, right? And then it goes through y of s. Versus closed loop, it would be our input, and then it would go through to a summing block here. And this would be b over s plus a, our transfer function. And then it would lead to our output y of s. And then here it goes backwards, okay? So what we have to do is, looking at this, our transfer function basically for the system is given by g of s is equal to b over s plus a. And if you are to normalize this, you're going to get, if you want +1 in your denominator, it's going to be s divided by a, right? But if you need to divide the numerator and denominator by a, so it'd actually be, what you're going to have here is b over a if you divide that numerator and then just multiply by 1 over s over a plus 1. So here, if you have to determine the Bode plot of this, what we're going to see is it's going to have a constant value here, and then it's going to have a pole at A. And so that's where it's going to start decreasing by negative 20 dB per decade, but it's going to originally start at 20 log of B over A. So that's what we like about this one, is we're going to see that it's going to start at 20 log of B over A. Then it's going to minus 20 log, and then it's going to be square root of R, and then it would be omega divided by A squared plus 1. And so that would be the magnitude response if we're just looking at that. Where other one here, our transfer function, t of s, is going to equal. If you solve this, it would be b over s plus a plus b. Okay? And if we want to normalize this, we're going to divide a plus b. So if you think about this basically as, like, let's say you call this x, divide numerator and denominator by x, it's going to be b divided by x, and then 1 over, and then s divided by x plus 1. And then substitute what you have for x in here. So it'd be b divided by a plus b, and then 1 over, and then it'd be s divided by a plus b plus 1. Okay, so that's what you have here. Taking the 20 log of that, so 20 log of gj omega is equal to 20 log of b over a plus b. And then you're going to have minus 20 log, and then it's going to be, here, what you're going to have is omega divided by, and then it's going to be a plus b, and then squared plus 1, and then square root of all that. Okay, so we're going to notice that this one occurs at a plus b. That's the corner frequency where it's going to occur, where this one occurs at a. And so if we look at the Bode plots, comparing the two onto one Bode plot, what we're going to analyze is one is going to start at 20 log of b over a, and the other is going to start at 20 log of b over a plus b. And so this one's going to be divided by a greater number, so it's going to start at a smaller response. compared to this one here. This one's going to start higher up because it's only b over a. This is divided by a larger number, so it's going to start at a smaller value. And so what we're going to see here basically is, let's first plot the open loop system. So it starts at a higher value, we know, and then it's going to, at a, that's our corner frequency where the pole is going to occur. So it's going to start to drop negative 20 dB per decade, okay? So that's going to be, so it starts at 20 log of b over a, and then it drops at a. That's where it starts to drop negative 20 dB per decade. Where the closed loop system is going to start at 20 log of b over a plus b. So it's smaller, the number. So it's going to start smaller. But this is going to be at a plus b, where the corner frequency is going to occur. And so then it will start declining negative 20 dB per decade. So notice that it starts a little further in terms of its decline. Like it has a smaller DC gain, like at zero frequency, because it's b over a plus b. But notice that the corner frequency is further. So what we're going to determine, if you measure the bandwidth is to that corner frequency, which is the negative 3 dB point. So here the bandwidth, what we're going to notice, it's going to be up to that. For a first order system, it goes right up to where it occurs, where the bandwidth of the closed loop system is greater. We notice that the bandwidth to the negative 3 dB point, which is the corner frequency, is greater for closed loop system. So closed loop systems have a larger bandwidth, which means it's faster, but a smaller bandwidth means you have less noise. So the open loop system's nice in the sense that when you have a smaller bandwidth, you're not going to amplify high frequencies because this is your omega, right? It's going to be pretty much cut off. Excuse me, eliminates high noise. Where your larger bandwidth, what we're going to see here is a larger bandwidth contributes to a faster system in terms of settling time, rise of time, etc. There you go. So that's what we have. So now that we determined that, what we're going to want to do is then, if you have a second order system, just remember basically your second order is going to look something like this. And so an open loop versus closed loop. And so we're going to see that, remember, our closed loop system here, it has a larger bandwidth. Our open loop system has a smaller bandwidth. Notice that the 3 dB point is going to be smaller here. But what we're going to have here is we're going to see that what's nice is it's going to have less noise at the end because it's not going to amplify. But the open loop system starts at a high magnitude compared to the closed loop, which we saw it was a smaller magnitude. And so that's why we like open loop, because if it starts with a high magnitude, it's going to be less steady state error. And so there's going to be less steady state error if you start higher up. And so that's what we're going to notice. So we're going to loop shape the system to try and get it to start at a high magnitude. Okay, so now that we determined that, what you're going to notice with a second order system basically is second order systems sort of have like a little bit of a peak when you do the Bode plots of them, depending on your value of zeta. So for your second order systems, remember like how your second order systems, like the transfer function is written as omega n squared all over and then it's s squared plus 2 zeta omega n s plus omega n squared. Okay, so basically with the second order system, what we're going to realize here is that you're going to see specifically, depending on your value, the damping ratio. If you have a smaller damping ratio, your plot is basically going to have more of a curve in terms of its right before the negative 3 dB point. So a lot of times you start at 0 dB. So here, this is 0 dB. And if you normalized it, it's going to look something like this, your second order system. And so it's going to have a little bit of a bump for small values when zeta is a small number. So like less than 0.5, we're going to notice that you're going to have a bump here. And so your negative 3 dB point is out. So this would be like negative 3 dB per se, if it would be like around here-ish. So that's where your bandwidth is from basically to your negative 3 dB point. And so at this peak value, what we like to call this, so you know, is it occurs at the resonant frequency. And so this is known as the MP omega, the max peak value. If you're talking about it on the magnitude plot, this would be 20 log of MP omega. But what we're going to see is then this frequency right here, when you hit the negative 3 dB point, that's known as your bandwidth. So omega B. And so what we're going to see here is second order systems have a little bit of a curve for small values of zeta. So zeta like less than 0.5. So what you're going to notice is they call this the resonant frequency. So the resonant frequency here is when your second order system, because a lot of higher order systems can be approximated by second order, correct? So the resonant frequency omega r is equal to omega n square root of 1 minus 2 zeta squared, for zeta less than 0.707. And so here, make sure you know that your resonant frequency, that's when you hit your peak value. And your peak value, which is your MP omega, is equal to, and then this is going to be 2 zeta square root of 1 minus zeta squared. And then you take the inverse of that entire thing. And so same thing, this is for zeta less than 0.07. 07, because that's when you actually have a peak value, and that's when you actually have like a resonant frequency. And so like that bump actually occurs when your zeta is less than 0.707. Otherwise, the bump's not there. And so then you wouldn't have like a peak value or a resonant frequency. And so that's basically two really important things what you're going to notice. And so we'll see here with the second order systems that when you have small values of zeta, for 0.1, 0.2, 0.3, you have larger bumps here for your response. When you have zeta like 1.0, it's going to be like a normal response. And so what we're going to notice basically is if you have a smaller zeta, so 0.2, you're going to have a higher resonant frequency, and you're going to have a higher peak max peak value when you have a larger, and when you have smaller zeta, you have a larger peak, as we see from this graph here. And you're going to have basically, you're going to notice that your natural frequency approaches your resonant frequency. And then when you have a smaller zeta, so if your zeta increases, so if you have a larger zeta, you're going to have no peak here, basically. And so we're going to see there's like 0 peak. The peak is basically like 1. It's unity. You don't have any gain really in there, like no peak. It's just 20 log of 1 is just 0 dB. And so that's what you'll notice. And then we like, but when we do have a smaller zeta, we have a bit of overshoot as seen here. So just know that you do have overshoot. And so now let's talk about gain and phase margin, because those are really important to talk about. These are going to determine the stability of our system. And so let's look at those two and how they operate. So gain margin is defined as G of M. So this is gain margin. It's basically changes in the, and it refers to open loop system. You analyze the open loop system for the gain margin and the phase margin. You don't analyze the closed loop system. So changes in the open loop system at phase equal to negative 180 degrees to make the closed loop system unstable. And then for phase margin, what we're going to notice is the phase margin, which is defined as phi of m, phase margin, is the changes in the the open, because remember, they both look at the open loop system at gain is equal to 0 dB to make the closed loop system unstable. Okay, so let's look at an analysis of this, basically on the gain margin and phase margin plots. So if we're looking at the open loop system, so here's our magnitude and our phase plot. So here we're going to have specifically our omega. Okay, so this one is at the 0 dB point, and this one's at negative 180 degrees. Okay, so when we cross the 0 dB point, this is known as the crossover. You're crossing over, basically, and so it's known as the crossover frequency. And let's say that you have your phase plot here. So bringing down from this crossover frequency, we look at what's the difference here. This is known as specifically your phase margin. When you cross the 0 dB point, that's how much phase you have here, is known as your phase margin, where when this line intersects specifically with the negative 180 point here. So at this negative 180 point, that determines your gain margin here. So your gain margin is determined when you cross through the negative 180 degree point on your phase plot. And so that's what we're going to see here. And this is all dealing with the open loop system. When you plot it, you're going to notice when you cross 0 dB, that's going to determine your phase margin. When you cross negative 180, that determines your gain margin. And we're interested in the 0 dB point because remember, 20 log of 0 dB is 1, right? And then negative 180, so on the unit circle, isn't that 1 at negative 180 degrees here? That is our Nyquist. Remember, we were so concerned with how many times we encircled this, because this is what's going to make your system basically unstable. And so that's what we want to avoid, is crossing this point here. And so that's what we want to avoid. So we want to avoid this plot. So this is the amount of margin we have before a system becomes unstable. And so that is very important. That's why we like looking at gain and phase margin, is we want to avoid that plot, that specific point. And so now we're going to look at the unity feedback system, and we're going to determine the range of K for which the system is stable. So let's look at the example. So if we have R of S, it's unity feedback. So here, what's going to happen is we're going to have our G of S, and then it's going to go to our output C of S. And so G of S is going to equal K all over S plus 2 times S plus 4 times S plus 5. Okay. So it says determine the range of K for which the system is stable. So determine K for which the system is stable. So if we have to determine K for which the system is stable here, what I would do is I would be like, okay, if I know this, remember, I have to determine stability. So I'm going to look at my gain and phase margin here, in order to try and determine it. So let's look first at the open loop system from MATLAB, and let's try to determine the gain and phase margin from the Bode plot. And so remember, you could do specifically, like we saw root locus, and you can make like a phase lag or phase lead compensator. But here we're going to try and determine from the Bode plot. So they're both tests for stability. So let's look at MATLAB. So I'm going to clear everything here. And then I'm going to use S is equal to the transfer function of S. And so here, if we need to determine K for which this system is stable, you probably remember basically what we need to do is our Bodhi. So we need to make our G is equal to, and then here we don't know the value K. So we're trying to determine that. So now it's just going to be 1 divided by S plus 2 times, and then here we're going to have S plus 1. And then we're going to have times S plus, let me see, S plus, oh, sorry, this is 4, S plus 5. Okay, so that's going to be our system. We're going to plot the Bodhi of the open loop system. Okay, so here, what I get as a result is it tells me the Bodhi plot here. And so I actually want to display the margins on here because that's going to make it a little easier. So I actually know when it's intercepting. So I'm going to sort of use this. If you can use MATLAB on the exam, why not tell you the gain and phase margin from the plot? So notice here it tells me my gain margin and my phase margin. So my phase margin's infinity, which is really good. That means I don't have to worry, but for my gain margin, I have about 51.5 dB. Remember, the gain margin is determined when you intercept with the negative 180 point, which we see right here when we intercept with negative 180 here. We're going to hit our gain margin, which as the system, what it said is it's about right here, which is around our negative 51 about dB. So that's how it determined it. It looked at negative 180 crossing and it saw what was the dB point. It's around like, if we look here, it's about like, let's see. Oh, sorry. Wait, real quick. It looked at the difference because remember, gain margin from here all the way up. So if this was our 0 dB line here, it looked at the difference between here. And so that's your gain margin. And so the gain margin is 51.5 dB. And so that's what we see. 0 minus negative 51.5 gives you 51.5 dB. So we determine our gain margin from here. So what we have to do now, going back, because we know our gain margin is 51.5 dB, we're going to determine, so if we know 20 log of K has to be less than or equal to 51.5 dB. Okay, because that's how much gain we can add before the system becomes unstable. So here we're going to have divide by 20 onto the other side. So it's going to be 51.5 divided by 20 is less than or equal to log of K. And then remember log, if you do 10 and then 51.5 divided by 20, in order to determine what K can go up to, here if we take 10 of 51.5 divided by 20, we get 376 about. Remember, your K starts from 0 and it goes up to that point. That's the max you can hit. And so that's about the max gain we can apply. And so now that we have that, that is our range of K for which the system is stable. And so what you're going to specifically notice is you can apply this much gain before your system becomes unstable. So that is really important to notice. So if we look at MATLAB, let's now do margin of 370. Let me just do 5 just to have one right under it. I just want to make sure it's hit. So let's look at this plot. I can get pulled up here because I have the window left open. Notice that our gain margin's really small, but we're still stable. We haven't gone negative. And so that is important, but notice that it decreased our gain margin a lot. So we're able to apply that much gain and we were still in the stable conditions. So that was really important here. And so now let's go back. Basically, because on my calculator it's at 375.83, so I would say that not including 376. I just say up to 376 actually, because I rounded it up to 376. So just be careful right there. And then now, what if they chose the gain to be 200? So what if K is chosen to be 200? Okay, so if K is chosen to be 200, we're going to decrease our gain margin. And so we need to calculate the new gain margin in order to determine what we can have. And so what we're going to do is we're going to have 20 log, and then we had our maximum gain margin, which is 376, divided by the K chosen, and that's going to determine our new one, which is 5.5 dB. So you do your max divided by what you choose. And so 20 log of your max divided by what you choose. And if we look in specifically MATLAB, if we chose 200 times G, what that gives us for the plot, it should match. Here, notice that the new gain margin is about 5.5 dB, which we calculated. So that is correct. So you do your max divided by what you chose. Okay, now that we have that, let's look at if you add in a delay to the system, how that impacts specifically your system. And so what we're going to want to notice is if we add a delay. So say if we have, so this would be the delays effect on the Bode plot. So this would be your RVES, goes through delay, and then goes through your GVES to produce your output. And then your output will be delayed, so you know. So remember that's like multiplication by an exponential term. That's going to be what your output is. So then to produce whatever output you have. And so we're going to notice here, when you do this, your delay, it's e to the negative st. That's a delay. It's an exponential because if you take the Laplace of a time delay, it's an exponential in when you do the Laplace transform. And so what we're going to notice basically is when we add a delay, it's going to decrease our phase margin, and it's also going to decrease our gain margin. And so what we're going to see here is when we have a delay specifically, if we have our GD, and then if we're looking at the frequency analysis of G J omega, it's going to equal e to negative j omega t multiplied by G J omega. And so if we look at the magnitude representation, the exponential does not change the magnitude, but it's going to add a negative omega t plus, and then the phase of G J omega. So we're going to add a negative omega t. So you're going to notice that your phase is going to decrease because you're subtracting a negative omega t. And what we're going to notice here is if you decrease the phase margin, what's going to happen in your plot? If you have the original gain and phase plot, your phase margin is going to decrease because what we're going to notice here is it's going to be subtracted by omega t, so it's going to decrease a little bit. And if you're decreasing, it's going to intercept at a faster point with negative 180, so your gain margin is going to be less than it originally was over here. So it's going to decrease both your phase and gain margin when you have a delay. And so big thing, what you're just going to notice is that the delay hurts your system in sense of it's going to shrink your gain and phase margin, and it's just going to make things worse overall. That's what you need to know. And so now that we talked about that, let's look at phase margin for second order systems. So for second order systems, the nice thing is that the phase margin can be approximated. And so what do we mean by the phase margin can be approximated? Basically, if you know your zeta for a second order system, it's going to be equal to the phase margin divided by 100. And this works for zeta is less than 0.7, less than or equal to. So you can approximate how much phase margin or what's your value of zeta. If you know your phase margin, you can determine zeta. If you know zeta, you can determine your phase margin. So it's like a general rule of thumb. You can approximate a lot of higher order systems by second order systems. So we like this general approximation. And so what we basically see is for the bandwidth of first versus second order equations. The cool thing for first order systems is the bandwidth is usually equal to 1 over tau. Because remember, for a first order system, g of s is equal to k over tau s plus 1. And so, wait, it's equal to s, and then that's b over, I was supposed to say, divide by, so it's 1 over, yeah, because then 1 over tau, if you remember first order systems, it's like a over s plus b or something. And then if you divide everything through by b, so a over b divided by, and then like s over b plus 1. And then we say that, hey, this is your k value. And then here, this is 1 over b is your tau value. So you say tau of s plus 1. So that's what we say 1 over tau. That would give you where your pole actually occurs. And so the bandwidth is equal to 1 over tau because we saw from the plot, literally when you plotted it in, this would be your 1 over tau point. That's where the negative 3 dB point is. So where it hits that negative 3 dB point. And so that's your bandwidth of your first order system. But for your second order system, your bandwidth, basically where this omega b is, which is 1 over tau for the first order, bandwidth is a little bit more complicated of an equation. It's equal to omega n 1 minus 2 zeta squared plus square root of 2 minus 4 zeta squared plus 4 zeta to the 4th. So that's your bandwidth of a second order system. And so that's what we're basically going to see here within our designs is the bandwidth of a first order is 1 over tau. And then for bandwidth second order, it's given by that equation. So your bandwidth frequency is where you hit that negative 3 dB point. And so now that we determined that, we're going to look at sensitivity. And so sensitivity is going to specifically tell you how sensitive your function is to a certain parameter. And so we're going to notice that sensitivity is defined as follows. And so your sensitivity so it's going to be the sensitivity of your transfer function for changes in A. It's going to equal the partial derivative of your transfer function with respect to the partial of A multiplied by A over your transfer function. Okay, so if they ask, for instance, so this is your general sensitivity equation. It just tells you the sensitivity of your function in response to if this variable A changes within your function. And so let's look at an example where we're going to have to see the sensitivity. And so what we're going to want to do here is, for instance, if we're given R of S goes into a summing block, and then it's going to be K over S times S plus A. And then it's going to go to our output C of S. And so here, if we have to determine the sensitivity of the closed loop function, so sensitivity of T of S with respect to changes in A. So we need to find the closed loop transfer function first. So T of S equals, it's going to be K over S squared plus A of S, and then plus K, basically, when you solve for it. And when we have to take the sensitivity, the transfer function with respect to a, it's going to be the partial t with respect to the partial of a multiplied by a over t. Okay, so we have to take the partial of t. I say rewrite this so it's simpler, as plus k to -1. So if you remember the partial of t with respect to a, that's going to equal, so taking the partial derivative of this, so you have two things. So you're going to do first times derivative of the second, and so we take the first, so that -k, because, and then we're going to have s squared plus as plus k, and then you're going to make this a -2, you decrease the power by 1, and then taking the inner derivative, and so we took the derivative of the outside, then we have to look at the inside. So derivative with respect to a, we have an s term, and then plus, and then it's going to be the second times derivative of the first with respect to a, and so then what we're going to get here specifically is this would just be 0 because k with respect to a derivative, that's just 0. So here we're going to get negative sk all over s squared plus as plus k, and then it's going to be squared. So that's our partial t with respect to a. And now we need to find a over t. So I'm going to plug this in. So my sensitivity of t with respect to a is equal to negative s of k all over s squared plus as plus k squared, and then times a all over, and then what's my transfer function? My transfer function was k all over, and then it's s squared plus as plus k. So we're going to notice that this one's going to cancel with this one here. And then we're going to have the k in numerator is going to cancel with k in denominator here. And so you're going to be left with negative as divided by, and then s squared plus as plus k. And so that is our answer for the sensitivity. So good job. That's pretty much how you find the sensitivity with respect to one parameter. Okay, now that we have that, basically, we're going to look at a little bit different of an analysis. So we're going to have the following system. And so our system's going to be given by an input signal, which goes to a summing block here. And then it goes to a control block. Then we have a disturbance introduced. And then we're going to have our system. Then we're going to have our output. Then we're going to have a noise block. And then it's going to be fed back to our input. Okay, so what's going to happen here for, oops, sorry, just N of S there. What we're going to have is basically we have an input, we have a disturbance, and we have a noise block here. And so we need to determine the output based on all those parameters. And so our output, if we look at just one contribution at a time, so making these 0, it's just going to be like our closed loop transfer function. So it's going to be k times g all over 1 plus kg, and then times the input. So it's going to be here we're going to have kg all over 1 plus kg times the input. Plus, now we're going to have this one, which it's going to be g all over 1 plus kg. And so it's going to be just rg all over 1 plus kg times t d of s. And then looking just at this one here, so blocking these two, it's going to be here minus, and then it'd be kg, because the minus here, kg all over 1 plus kg times n of s, okay? And so now that we have that, what we need to do is, if we're to solve this specifically, if we're going to do our y of s, we would say this is equal to, this is our open loop system, k times g. So I'll say L plus 1 times L R of s plus, and then it's going to be 1 over 1 plus L times G. So I just moved the G over to the right, TD of S, minus L over 1 plus L, and then N of S. Okay, so that's what I have so far. And so this one is specifically going to be what we're going to notice here is if you want to find the output over the input when the other two are equal to 0. So if these are 0 here, and you just do the output divided by input, you get L over 1 plus L, right? So that's your transfer. That's basically your T is going to represent your transfer function. And so if we know this is our transfer function here, so if we call this our, basically, if you have your Y of S, the side note, your Y of S over R of S, when you have your TD equals 0 and your noise equal to 0, you're just going to get L over 1 plus L. So that's going to be your transfer function, the output over the input. So we like to call this here just our T, and then of R of S plus, and then this is going to be known as the sensitivity, sorry, the sensitivity transfer function, and then G of TD of S, and then minus T, because that's minus T, and then N of S. So the sensitivity function is defined as the complement of the transfer function. So if you do 1 minus this, you're going to get 1 over 1 plus L of S. So this is your output, another way to write it. And so what we're going to see is basically with this function here, we want to amplify, we want to make sure our output matches our input. So these two match. So we're going to want to have this be 1 at low frequencies. We want this to go to 0 at low frequencies. Or 0 just in general, sorry, because this goes to 0. But notice that our noise, we want to make sure our input matches our output, so we want to be 1. We want to get rid of this term, so we want this to go to 0. But notice that our noise term is exactly the same as our input. So we want this to actually go to 0 at high frequencies. Because at high frequencies, that's when our noise occurs. So we want to try and eliminate it. So we want to design basically our controller so that this controller here is going to follow our input. It's going to reject the disturbance and it's going to reduce the noise. And so that's going to be what we're going to do in order to try and get our result. And so what we're basically trying to do within our loop shaping is we want to try and have, this is our open loop system. We want it to be high at low frequencies. We want it to be low at high frequencies. And so for a closed loop, it's going to follow this pattern. So we loop shape L in order to get the desired result. So as we notice here, our open loop versus our closed loop system, and then our sensitivity is just, remember, 1 minus, and then whatever our transfer function was, is it's just the complement. So basically, now that we saw that, that was a pretty good overview. So with this part, I'm just going to walk through within here because it's basically stated, I think, pretty good in the notes. For the Nyquist contour, it's basically the entire right-hand plane. And you're trying to do encirclements about -1. So feedback is stable if the number of counterclockwise of encirclements is equal to the number of poles you have. So number of counterclockwise encirclements, that's why there's a negative here to say if you have 5 poles, you should have 5 counterclockwise encirclements. So negative accounts for the counterclockwise. So 5 open loop poles, 5 counterclockwise encirclements. So you just try and encircle this point. If it's equal to number of open loop poles, then your feedback system is stable. And so remember in the night on the Bodhi plot, we wanted to avoid the 180 in the phase of 180 at the gain of 1, because that's where instability can occur. And so what we're going to see is that if we introduce a delay into the system, so here we're introducing a delay, we're going to see that the amount of gain that we can have here is going to be the gain multiplied by here, which we're going to see basically the magnitude, the exponential is not going to affect specifically, but it will affect our phase margin, because we're going to see that the phase, the exponential, has a phase associated with it. And so that's what we're going to notice here, is that phase margin will be affected. And so the delay that the system can handle before becoming unstable is given by the delay is equal phase margin divided by your frequency. And so what we look at within this plot is, for an open loop, we like the gain margin to be greater than 2. And so that's about 6 dB. We like the phase margin to be greater than 30 degrees. So this is what we try shooting for in our designs. And we want a high gain at low frequencies to reduce the steady state error. And we want a we want it to decline a lot after corner frequency. So we want a small declining slope at our corner frequency. And so when we hit that 0 dB point, we want to make sure that we attenuate those high noise signals. And then for the closed loop system, we want the peak to be less than 1.5 so we don't have much overshoot. And we want there to be a declining slope around our bandwidth. So we're going to try and aim for that. So what we're going to notice is, say we have the following system, and we want to determine the phase margin and the gain margin. So this is, I would automatically, if you ask for gain margin and phase margin, I would literally just plot the Bodhi, the margin of, and then just plug this into MATLAB. And so what we're going to notice is he did that. He just did the margin and he just plugged it in, gain margin, phase margin. So we're never going to pass negative 180 degrees because it's infinity. And then here's our phase margin. So they're both good. And so we're greater than the 30 degrees for a phase margin. We're greater than the 6 dB for an open loop system. But when we look at our Nyquist plot, what we're going to see here is that if you move it up a little bit, this point is going to come intersect with here. And then we're going to, if we apply some gain, we'll pass the -1 point. And so just notice that what this is trying to tell you is right here at this specific frequency, your system is close. There's not much phase between here and -180. So your phase margin, it's going to hit the -180, and it's going to actually cause your gain margin to be a finite value. So just watch how it's telling you, because if you apply a little bit of phase here, your phase margin, if you change it, it's going to cause you to actually have a gain margin. So Nyquist plot just shows if you change the phase a little bit, you're no longer going to have infinite gain margin. So your gain margin is very dependent upon your phase margin, which we don't really see here, because when we cross the -180 point, notice that it's very close here. So if you do if you decrease the phase a little more, you're going to hit, and your gain margin is not going to be infinity anymore, because you're going to have an intercept. So it's going to actually be a finite value. Okay, now that we covered that, we're going to look specifically at the following. So minimum phase versus non-minimum phase. Minimum phase is all the zeros are on the left-hand plane. Non-minimum if we have a 0 on the right-hand plane. And so what we're going to notice is non-minimum phase starts at 180 degrees. Because right here, if we're at 0 frequency, so right at this point, the angle here is going to be 180, and the angle of the pole is going to be 0. So it would be 180 minus 0, because this would be numerator, the 0. Where with the minimum phase system, it starts at 0, because you have a 0 here and a pole here. And what we're going to notice is basically when we're at 0 phase, both are at angle 0. And so that's important to realize here. And so what we're going to do now is we like basically having our behavior go in the same direction. So we want to go for the minimum phase. So that's why we like poles and zeros on the left-hand side, because we can add some phase to our system. So if we add some phase, we can increase the phase margin, increase the stability of the system, and get the design criteria we want. So we're going to now get into the phase lead systems. And so using phase lead with the Bode plot design. And so I'm going to pause the. So now we're going to talk about when we have to design simple gain using Bode. And so here, basically, when we have our input, remember, and so now we're designing in order to meet basically specifications. And so this is where we introduce our controllers or compensator GC of S. And then we have a system G of S here. And then we have the output, which is C of S. And we have an H of S block here for say, like in our open loop system. And then we close the loop. So then we make a closed loop system. So what we're going to do here is basically we need a plot if we're going to have to just do simple gain using Bode. So this is just for the simple gain using Bode. The first step is you plot the uncompensated system. So plot the Bode for the uncompensated system. So that is going to be your L of S is equal to G of S times H of S. Okay. Then we're going to determine the phase margin, how much we want. So number 2 is determine from here, we want to have our determine the gain and phase margins from the Bode. And what we have to do then is we have to find basically how much we need to add to give us the system that we want. So find basically at what frequency we meet the desired specifications. And then after that, the fourth step is we are going to basically determine the system gain. Okay. To shift the Bode plot up or down. If K is positive, we shift it up. Negative, shift it down. System gain K. So that would be in our controller. And so we just iterate then on the design. So let's do an example to walk through these steps and basically see how it works. So let's say that we have specifically here an input R of S. And then here it goes through a summing block. And we're going to have our K, which is our controller basically here. And then we're going to have 100 all over, and then we're going to have S plus 10, or 100, sorry, S plus 36, and just S. So I'm going to write that in here. So this is our G of S right here. And then our output is going to be C of S. Remember, your output's fed back to your input here. And so they want us to determine K so that, so determine your percentage overshoot is less than 10%. And your KV is greater than or equal to 10, okay? So what we have to determine here is from percentage overshoot, we know zeta must be greater than 0.6. And so if we know zeta must be greater than 0.6, we can approximate the system with the second order. So we can use the relationship that zeta is equal to the phase margin divided by 100. And so here, if we solve for phase margin, we're basically going to determine that our phase margin is going to have to be is about equal to 100 times zeta, which is 0.6, we can say. So phase margin is going to be 60. That's what I would do first. And then our KV. Our KV is going to be our velocity constant. If you remember, and the velocity constant is determined by, so your KV is equal to limit as s goes to 0, and then s, and then it's going to be your open loop system, which is k times 100 all over s times s plus 100 times s plus 36, okay? So what we're going to do here is we're basically going to have it, s would cancel the s, so you're going to get 100k all over 3,000, so 100k all over then 3,600. And remember, this is our KV, and our KV must be greater than or equal to 10. Multiply this over basically to the other side, and we're gonna get well, this would be K all over. And then here what I notice is that these would cancel, so it'd be over 36 is greater than or equal to 10, so it's gonna be K is greater than or equal to 360. Cool. So that's what we got for K. So we're able to determine what our K should be greater than. And so those are our design requirements. So let's plot the Bodhi, the uncompensated system. So just our G of S here. So when we plot the Bodhi of the uncompensated system, what we're going to see specifically in MATLAB is, if we clear everything, then we do S is equal to, and then transfer function of S. And then we're going to do G is equal to our uncompensated system, 100 divided by, and it's going to be S times, and then it's going to be S plus 100 times, then S plus 36. And then we're going to do Bodhi of G. Okay. Oh, I forgot. We can do margin of G because that will give us the gain and phase margin. So that would be helpful. Then we don't have to approximate it. And then here what we see in MATLAB is when we plot that, we get this figure. So going back to what we basically have here, so let me put that on the left-hand side, then let me put the work on the right-hand side. Okay, so what we have, basically remember our step 1 was plot the Bodhi, the uncompensated system. So our step 2, we determined that here, our gain margin is equal to 73.8 dB, and then at omega is equal 60 radians per second, and then the phase margin is equal to 89.9 degrees at omega is equal 0.0278 radians per second. Okay. So what we have to do here is we need to find the frequency where we meet the desired specifications. And so our specifications, we're asking for KVs greater than or equal to 360, and our phase margins equal to 60, or it can go down to 60. It can be, if we look here, if we have a higher zeta, we're going to have a higher phase margin. So we plugged in, so like our phase margin can be greater than or equal to 60, so we know. Because if you have, remember how phase margin and zeta are linked? If you have a higher zeta, you have a higher phase margin. And so our phase margin can be greater than 60. So we have some room. And specifically our gain margin, 73.8 dB. Well, remember when we calculated our K here, our K had to be greater than or equal to 360, correct? And so what we're going to notice is basically within our design, it wanted us to find basically from here, we did the K greater, then we found our phase margin. And so the gain margin and phase margin, does this satisfy our requirement? Is the overshoot less than 10%? And so overshoot our KV, and then no space. So we do have some room to add some gain to the system without disturbing the system's phase. And so what we can do is we want to find the max amount of gain we can add to the system. Because we said that KV is equal 360, but we notice that the gain margin isn't infinite. So we notice that there has to be a limit to how much we can add specifically to our system. And so what we're going to do is we're going to want to look at specifically our max gain margin. Let me see if we do, why did we set it equal 55? Give me 1 second real quick. Set it equal 55 to the max. What's we want to do? Wait, where we have 60. Okay, our phase margin must be greater than or equal 60, correct? And so if we look at our Bode plot here, if we're gonna decrease our gain, if we decrease our phase margin to get, so if our phase margin changes to 60, so that's when it intercepts with the 0. So basically from here around like -120, which I'm assuming is in between here, so up 20-ish, it would be around here-ish. So this would be like around where we intercept if we change our phase margin, so that this is around where we would now hit, because remember the phase margin is the difference between these 2 points here, because it would be, if our phase margin can be about 60 degrees, we have to be greater than that. So this is the smallest phase margin we can be at for 60 degrees right here. And so if we need to find out the maximum value gain, we're going to do the smallest amount of phase margin. And so at that smallest amount of phase margin, this is around like 14.5. What we notice, it's in between 10 and 20 here. And so we're going to find that our omega is around like 14.5, and the phase is about like 120 degrees. And when we look specifically at the gain at that state here, it's around going to be -55 dB. And so here it's going to be like around -55 dB at that frequency. So that's what we see specifically is the amount of gain we can go up to. So our 20 log of K, how much gain we can have is equal to, and then here it's going to be 55 dB. So if we do K, if we're trying to solve for K, if you do K is equal to 10 to the 55 divided by 20, what we're going to get here is it's going to be 10 to the 55 divided by 20, which we get here 562. So, and so our K is going to be limited between the values of, and we determine here 360 for K, and then it can go all the way up to 562. That's what we saw pretty much. So let's look here. We should be okay in terms of getting our phase margin is still above 60 degrees, because we had some room. We could decrease our phase margin. And so if we decrease our phase margin to the smallest it can be, which is 60 degrees, we saw that that point where our phase margin became 60, so that -120 point was like around here-ish. So we saw is around like 14.5. And then we looked at how much gain do we have there. It's like -55 dB about when we do the intercept. And so we set 20 log of K is equal to 55. And then we're able to determine the max value K, it's about 562. And so since we know the max value of K, what we're going to do within here is then if we do margin and then we do 562 times G, are we going to see it? So this plot should represent, let me check it. Here, our phase margin's right at 60, so that's the minimum. And then our gain margin here is at 18.8 dB, what we have. So how much gain left you can apply. But notice that our phase margin is 60.1. And then that would satisfy basically the most amount of gain in our system is still satisfying within both those regions. So we found our limits of our gain by just the minimum gain we had to hit by satisfying that velocity. And then we satisfied specifically the most amount of gain we can add in order to maintain our requirements that our phase margin stayed above 60 degrees. And so that's what we did here. And now that we determined that, our next step is going to be using first order compensators. And so let's get over here real quick. And so first order compensator, oh, let me reshare. I don't know if it's sharing my screen, so I'm gonna just reshare this. So what is going to happen with a first order compensator is basically we just looked at simple K right there. But a first order compensator, what we actually have to determine is it's in the format GC of S is equal to K times S plus Z all over S plus P. So we have a lead and a lag compensator. So we're going to focus on phase lead to start out. So you guys know, and so phase lead is important. And so let's look at how we're going to solve a phase lead system. So let's look at a phase lead compensator. And this is design using Bodhi. So, you know, phase lead compensator using Bodhi. Because we looked at earlier in this lecture using root locus, but this one will be using the Bodhi plot technique. And so the first thing is you need to determine right here, they call this KC within the compensator, like the compensator gain. So determine the compensator gain. So the DC requirements, which is known as the steady state errors of the open loop system are satisfied. And then the second step is basically we're going to evaluate the phase margin. So phase margin of the uncompensated system. So this is where we plot it. And so we're going to look at the phase margin. And then we're going to allow for some extra phase. And so we like to add more phase than less, so extra margin. So this is about 5 to 12 degrees. I usually always stay on the safe side and add more phase, so I add 12. And determine the needed phase. Needed phase lead. So that is phase margin max. Okay. And so the max amount you need to add to the system. And then you determine the value of alpha from the graph. So alpha is the distance between the poles in 0, because in a compensator you have a pole in 0, so alpha from the graph. So make sure you have that graph handy. Then the fifth step is you're going to pick omega max as the crossover frequency. Crossover frequency. And then what we do after that is we're going to draw a new Bodhi plot. And so we're going to just check the compensator. So basically what you do here is you draw the compensated response. So the Bodhi plot for the compensated response. And then after that, what you're going to do is you're going to just iterate on the design. Design. Okay. So that's pretty much what you have to do. You just go back and reiterate. So let's look at what we need to do. So let's look at an example where we need to apply all these. So for our example, we're going to have the following system be given to us. L of S, which is an open loop system, is equal to 1 over, and then it's going to be S times, and then S plus 2. So here it says design a phase Lie compensator. So the air steady state to a ramp input is equal to 5%, and the phase margin is greater than or equal to 45 degrees. Okay, so for our design requirements, the air steady state, remember, if this is your air steady state is equal to 0.05, remember, for your ramp input, it's 1 over kV is equal to 0.05. If you multiply, kV is equal to 1 divided by 0.05, so it's equal to 20. That's what's telling you. And then the phase margin, remember, your phase margin, your zeta value is determined by your phase margin here, divided by 100. So if you have your phase margin can be greater, so it'd be 45 divided by 100, so 0.45. Zeta can be greater than or equal to 0.45. And so what we see from this is we need to determine KC so the DC requirements are satisfied. So what we know about our KV, remember KV is equal to the limit as S goes to 0, S of GC, your compensator of S, times your open loop system. And so that needs to be set equal to 20. That's what we found out KV needs to equal. And so what we're going to have here is our L of S is 1 over S times S plus Z, and then our GC of S, and then multiplied by S, and limit as S goes to 0 is equal to 20. And so here we're going to have the S's cancel, and it's going to be GC of 0 all over 2, which GC of 0 is going to equal 40 basically here. And then what we're going to see, if it's GC of 0, remember that means you just have your KC, and then it's going to be your KC right here, because the other ones would be S plus 1. Okay, yeah, because remember your GC, it's written in the following format: plus 1 all over, and then it would be tau S plus 1, where these would just cancel. And so it's just equal to 40, because this would be 0 over 0, 1 over 1 would be 1. So it's just KC is equal to 40. Okay, so that's what we know. So we know our KC must be equal to 40. So we're going to evaluate now the uncompensated system. So when you evaluate the uncompensated system, you're going to do margin, and then you're going to do the KC multiplied by your L of S, so you know. So let's look at, because you already know what your KC is, so you're just going to plug it in. So S is equal to transfer function of S. Then we know our L is equal to 1 divided by, and then S times S plus 2. And then we're going to have margin, and then it's going to be our KC, which is 40, times our L. So here we know what our gain margin and our phase margin are equal to. And so then what we see here is that we know that our phase margin must be greater than or equal to 45. So right now we're not above 45. What we see from the plot here basically is our gain margin is equal to infinity, but our phase margin is equal to 18 degrees at omega is equal to 6.17 radians per second. Okay, so what we're going to have to do here now is going back to our design, is we need to determine how much phase we need to add. So the phase margin, basically this would be step 3. The phase margin max that we have to hit. So remember, we have to be above 45. That's what the design requirements we're wanting. So in order to be above 45, so we want to hit 45. We're already at 18, so we can subtract that. And let's just add some extra phase. I'm going to add 12 degrees. So we hit that. So we'll be about 39 degrees is what we need to add here. And so we're going to add 39 degrees. And so we need to determine alpha from the graph. So if we choose 39 degrees, we're going to add, that's about alpha is equal to 4.5 here. So you use the graph, and you say that alpha is equal to 4.5. Now, what we need to do is we need to pick the omega max to be the crossover frequency. So what is our omega max going to be here? And so our omega max, what we want that crossover frequency to be is where phase margin occurs is about 6.17. So we're going to just have that because that's the crossover frequency. So our omega max is going to equal the crossover frequency. And so knowing that our tau is equal to 1 over, and then it is going to be our omega max square root of alpha. And that's going to equal 1 divided by 6.17 square root of 4.5, which is going to equal, so 1 divided by, and then it's going to be 6.17 square root of 4.5. You're going to get this is equal to 0.0764 for your tau. And now that you have that, now you're going to make your compensator. So your compensator, which is GC of S, we knew the K of C from the beginning, which is 40. And then remember, your compensator, I'm just going to write this on the side, your GC of S is equal to, and then it follows the format KC, and then it's alpha tau of S plus 1 all over, and then it's going to be tau of S plus 1 in the denominator. And so here, it's going to be KC times alpha, which is 4.5, times tau, which is going to be 0.0764, and then S plus 1 all over tau, which tau is 0.0764 S plus 1, okay? And so this is going to equal, and so here we're going to have 40, and then in the numerator it's 4.5, times, and then 0.0764, we're going to have 0.3438 S plus 1 all over in denominator. We're going to 0.0769 S plus 1. Okay, we're almost done here. So this is our compensator that we have. And so now we're going to plug that into MATLAB, and let's see what we get specifically. And so here, I'm going to make my compensator. So my G of C is going to equal. And so it's 40 times, and then it's going to be 0.3438 times S plus 1 divided by 0.076 or 0769 times S plus 1. Okay. And then we're going to do margin of L times G of C, because your open loop system times your compensator. And so the phase margin needs to be greater than or equal to 45 degrees. That's what we need to see here. So when we do the margin, what we're going to get here is, notice that our phase margin is greater than 45 degrees. So we satisfied our requirements. Good job. Now that we got that, we're going to look at the next one. This is pretty much our last example, and then we'll be done. So let's start with this one, and we'll see what we need to do. So this one is asking for specifically, we're going to have a unity feedback system. And so for this example, we're going to have R of S. It's going to go through. And then we're going to have our K of S, then our G of S, and then our output C of S. And so what we need to do is within this system here, this is going to be tied back here. So our G of S is equal to, and then 1 over S over 0.5 plus 1. And then times S plus 1 times S over 2 plus 1. And then here, we're going to design the compensator K of S. So design K of S. so that the phase margin is at least 25 degrees and the position constant is equal to 9. Right? And so what we need to do here is we first need to determine our requirements. So remember, the position constant, Kp, is equal to the limit as s goes to 0, and then it's going to just be of your g c of s times g of s is equal to 9. So that's what we know. So here, what we're going to have is, remember, our GC of S is going to be our KC times alpha tau of S plus 1 all over tau of S plus 1. And then our G of S is going to be 1 over, and then it's going to be S over 0.5 plus 1 times S plus 1 times, and then it's going to be S over 2 plus 1. And then here, so this is limit as s goes to 0, and then all that's equal to 9. And so when s is equal to 0, it's going to be kc, and then it's going to be 1 over 1 times 1 times 1. So kc is literally going to equal 9. Okay, so that's what we see here. And then now we determined our constant. So what we need to do here is we're going to evaluate the system. And so we're going to evaluate specifically the phase margin of the uncompensated system. So we're going to do margin in MATLAB of the KC value, which is 9, times our G of S. And so when we do that within MATLAB, going over here, because that would be our uncompensated system with the KC, we're going to get we need to do our S divided by 0.1. Okay, and then we need the margin. KC was 9 times G. Notice that here from our system, we're going to basically find out that our phase margin and our gain margin. So I'm going to write those down. The gain margin is equal to 1.494 dB at omega is equal to 1.87 radians per second. Okay, my phase margin is going to equal 7.13 degrees at omega is equal to 1.68 radians per second. Okay, so what I can determine here is our phase margin is not met. It needs to be greater than 25 degrees. So what we're going to do here is switching over, we need to, the third step, you are going to find how much margin you need to add. So the phase margin max you need to add, well, we need to at least achieve 25 degrees minus what we currently have, 7.13 degrees, and then add 12 more degrees for some extra margin. And so this is going to equal, if you do this on your calculator, 25 minus 7.13 plus 12, I get 29.87. So that's how much I need to add. And then determine alpha. So if we have 29.87, looking at my graph for alpha, what we need to do specifically is that 29.87, it's about 3, we'll say. So alpha is going to equal 3. And then knowing that, now we need to pick omega max to be the crossover frequency. So crossover frequency is when your phase margin, that frequency. So omega max is going to equal 1.68. Okay. Now that we know that, now we need to draw the Bode plot for the compensated response. So our compensator are basically K of S term. The KC is 9, and then we're going to have our alpha, which is 3 times tau, which is, oh, we need to determine tau from our omega max. Remember, it's 1 divided by omega max square root of alpha. So that's going to give us tau's equal to 1 divided by 1.68 times square root of 3. That gives me 0.344. So 0.344. So alpha tau s, and then plus 1 all over tau s. So our tau is 0.344, and then s plus 1. Okay. So there we go. So now our k of s, if we solve that, it's going to equal 9 times what's in that numerator? It's times 3 of that. So 1.03 s plus 1, and in my denominator is going to just be the 0.344 s plus 1. Okay, so now we got our k of s term here. And what we got to do is we're going to plot our compensated system, so margin of k of s times, and then our g of s in MATLAB. So we're going to evaluate if it meets our phase margin requirements. So we're going to go over here, and we're going to have our k is equal to, so it's going to be 9 times, and then we're going to have 1.03 times s plus 1 divided by, and then we have 0.344 plus 1. Oh, times s. Okay, 0.344 s plus 1, 1.03 times s plus 1. Okay, and now when we evaluate the margin of this, so if we do margin of k times g, what we're going to see here is we didn't meet our phase margin. We hit 15.2, we're supposed to hit greater than 25. So what we're gonna do is we're gonna increase this even further. So we need to iterate on our design. So the big thing is I'm going to choose that, so going back here, we did not meet our design requirements. So I'm gonna redo step 3. So I'm going to make my theta m max. I'm going to increase it even more. So I'm going to make it 55 degrees because we noticed if you increase it up to like 55, you're about here. So that's about like alpha is equal to, I think it's, when I look up graph here, it's around 9. So I'm going to then, when we have that, our alpha is equal to 9. That's what we see from here when we hit 55. And then now that we got that, what we're going to do is we're going to determine our omega max. Our omega max, we're going to shift it over to the right a little bit. And so when we shift it over to the right, it's moving the 0 over to the right-hand side. And so the 0 is going to have a more dominant effect. So it's going to make the system more stable. So it's going to increase the phase and the gain margin, if you think about it that way. And so if we move it over, it's going to be 5. And so we're going to try that. And so then what we're going to have here is if we solve for a tau, remember tau is equal to 1 over 5 and then square root of 9. And so that's going to be 1 divided by 5, square root of 9. So 0.066 is going to be our tau 7. We can just leave it like that. And so now solving for our compensator, our k of s is still going to equal 9. And then tau times alpha, so it would be 0.0667 times 9. We get 0.6. S plus 1 all over, and then in our denominator, it's going to be tau of s, so it's going to be 0.0667 s plus 1. Okay, so let's try this new compensator. So going over to MATLAB, let's see if this works. So we're going to do our k is equal to, and it's going to be 9 times, and then 0.6 times s plus 1 divided by, and then it's going to be 0.0667 times s plus 1. And then now we're going to evaluate the margin of k times g. Looking at what we have here, our phase margin is greater than 25 degrees. So we satisfied, and it's a stable system. So we are good to go. That's pretty much it on how to do that. So that covers the phase lead for design using Bode plots. And that will conclude the session. So let me stop the recording.